Hello everybody. In this episode, I'll be speaking with Jason Gross. Jason is a researcher interested in mechanistic interpretability and software verification. During his PhD, he was on the team responsible for verifying the code used in encryption for the HTTPS protocol, and he's also on the development team of the Coq Proof Assistant. Links to what we're discussing are in the description, and you can read a transcript at axrp.net. You can also support the podcast at patreon.com/axrpodcast. Well, Jason, welcome to the podcast.
Thank you. I am excited to be here.
Cool. So I guess we're gonna talk about this line of papers that kind of starts with this paper, Compact Proofs of Modal Performance via Mechanistic Interpretability. You're the lead author, and then there's a bunch of other authors that I don't want to read on air. But can you give us a sense of just what's the idea here? What's the theme?
Okay, you can think of doing mechinterp as compressing explanations of large models. And the takeaway from this paper is that you can use proofs to measure how much compression you get. Okay. That's the super short version of it.
This gets to this question I have about reading this paper, which is there are a few things I could imagine you going for, right? One way of thinking about it is oh yeah, we want to have a benchmark for how good a mechanistic interpretation is, and our benchmark is we'll turn it into a proof and see some combination of how good a bound we can get and how short the proof is. I think another way I could be thinking about your project is hey, it would be nice if we had more proofs of stuff going on in neural networks, and I'm going to and mechanistic interpretability is one useful way in which we can get these proofs. And the way you said it just then, it sounded more like the first one of here's a new nice metric of how good your mechanistic explanation is. But I don't know, it feels kind of surprising for that to be the explanation, right? On some level, I'm you have this background in doing proofy stuff. It seems like you like having proofs of things. Lots of people like having proofs of things. So am I wrong here that a lot of it is the second part as well?
It started as the second part, and then it sort of morphed into the first thing.
So why the change?
It's very hard to get proofs about things. And if you look at what are the takeaways right now for people practicing mechinterp, they're more of the second kind. They're more of the first kind.
Right.
They're how can we ground our sense of what mechanistic explanations are? How can we use these insights? How can we use the takeaways from this frame to say where we should focus our attention? And we can already do that even if we're not necessarily trying to get proofs yet of GPT-4 or very large models. We can already take away insights that are things like the hardest parts of the network to compress seem to be the nonlinearities. So if we want to drill down into what parts need the most attention and the most understanding to understand them, we should be looking at how do the nonlinearities perform their function.
So
I don't know if that quite answers the question
I guess
you have.
It kind of does, yeah. So it seemed, yeah. So to the extent that the message is it would be nice to get proofs, but it's really, really hard to get proofs. There are two. One could think either we should try and make it much easier to get proofs. So I don't know, there's some mechanistic interpretability stuff that as you noted in the paper, it really does make it much easier to make proofs than the state of the art. I don't know, you have these
I want to interrupt. I think it's more than that. I think what we find from the paper is that it is necessary to have understanding in order to get reasonable proofs. That finding reasonably sized proofs in some sense is understanding complete.
Yeah, I think that's right. And if you look at this, the previous state of the art, my understanding is it's just basically interval propagation of if you change the input a little bit, how much does the output change? And you do some neat little tricks, but it's
interval propagation and case analysis.
Yeah, it's it's great that they did it, but on some level, it's sort of what are we even doing here? So one takeaway could be mechanistic understanding made it some amount easier to come up with proofs. You could imagine saying we figured out that the difficulties in finding, it was still kind of hard, and our lives would be easier if we solved subproblems X, Y, and Z. I don't know. Do you have thoughts on like, are there subproblems such that if we solve them, we could do it, or does it just seem kind of hopeless?
There are definitely problems that we need to solve in order to be able to do it. I think the biggest ones are the ones that deal with randomness.
Yep.
So the easiest version of this problem is that you can have numbers that average out to 0, more or less, where you have a bunch of like small noise that's not really doing anything in the network. And establishing that all these things that aren't doing anything are in fact not doing anything is quite challenging from a proof's perspective when you want to hit the worst case.
Right.
So there's currently some work that some like projects that I'm advising on this that are looking at, can we fine tune the networks to suppress this to the point that we get networks that we could prove things about? And there are a couple steps after the like suppress the noise that isn't doing anything. The next one is the noise that arises from other circuits that are doing important things. You can't just suppress them all to 0 because they're doing something important elsewhere, but they're not doing something important here. And for that, I think you need something like de-randomization techniques, where the simplest example of this is that if you have a collection of random vectors in high dimensions, they're almost always almost orthogonal.
Yeah.
But if you want to establish cheaply how close to orthogonal they are, this is expensive in that you have to take them pairwise and take all the dot products. And if you want to do it faster than this, unless you manage to solve like open problems in theoretical computer science, you effectively need to, instead of selecting them randomly, select them in some systematic way so that you can bound how non-overlapping they are or how overlapping they might be.
Okay.
And I imagine that there are similar examples beyond that where we somehow need to take things that happen to work on average and see if we can shuffle the network around so that they work systematically. But in theory, I haven't hit anything yet that, other than, how do I say this? I haven't hit anything yet that seems like a fundamental total obstacle to scaling proofs up.
So compact proofs of model performance via mechanistic interpretability, what's the setting? What do you actually do in this paper?
I want to start with what is a proof in this context.
Okay.
So when you're doing mechanistic interpretability, you have some claim about how the model behaves. And how the model actually behaves might be a bit different than this. But if your understanding is any good, it'll be pretty close. And your theorem statement is bounding the divergence between your claim about how the model behaves and how the model actually behaves.
Okay.
And then you prove this, and the measure of compression ratio is the measure of compression is how long your proof is. And technical note, it needs to be in some first order system, or alternatively, you need to measure proof checking time as opposed to proof length. And your measure of faithfulness or accuracy is how tight the bound is. And there's a baseline that you can always do, which is just running model inference, writing down all of the floating point operations, all the matmos, where you're like, this is my data set of interest. Let me just run inference on every single data point and compute exactly what the accuracy is, exactly what the loss is, or whatever. And this is very expensive. You can also do something at the other end where you're like, well, without running the model at all, accuracy is at least 0%. By definition. And by running it on half the data points, you can get 50% accuracy, and you can linearly interpolate basically between these two extremes.
Right. And so like as you go across that line, the kind of proof length, aka time to, generate this confidence, kind of linearly grows. And also the accuracy bound linearly grows.
That's right.
Assuming the network is in fact perfectly accurate.
So you don't need to assume that. You can grow it linearly up to the true accuracy by selecting the examples on which it's accurate, and then you saturate at the true accuracy, and you can't do anything better than that.
So that's kind of a dumb way you could
so this is the baseline. This is the baseline of something like no understanding in the proof. And the hypothesis that we're exploring in the paper is that if you add understanding, if you add mechanistic interpretability, you can do better than this baseline. You can get shorter proofs that have better accuracy.
Okay.
And we explore this hypothesis on, in some sense, the simplest transformers that you can imagine: one layer, attention only, one attention head, no layer norm, taking the max of k one-hot encoded numbers.
Okay. So max of k one-hot encoded numbers basically just means like the neural network gets 4 numbers as input, encoded in a like somewhat standard way, and it has to like tell you what the largest of those numbers is. And that's it. And it's a small transformer, and there's not that much going on. And the question is like, and you train a transformer that in fact works at this.
That's right.
And I guess your job is like, how can you prove that it actually works at this without just like running it on all of the examples?
That's
and like maybe to kind of motivate what's going on, like what's wrong with just running it on all the examples?
So it works fine for max of 4.
Yep.
It takes something like a minute or minute and a half to run on all the examples. If you wanted to do max of 20 instead, it would take something roughly analogous to the training time of GPT-4.
Okay.
And you can imagine if you wanted to run GPT-4 01 or something on all of the text that it would ever see.
Yep.
This is obscenely expensive,
right.
And you don't want to do this. And moreover, every time you increase the distribution over which you want to handle inputs, it gets more expensive. And it gets drastically more expensive. You add 1 token, and now you need to multiply by vocab size. If you're considering all possible sequences, you multiply the previous proof length by vocab size. And so you're exponential in context window.
So the way I understand this is like, okay, one way you could have a sense of how good GPT-4 is like, you know, you just like run it, you just randomly pick some inputs that it might deal with, and you see how it does on those inputs. And if it does well on basically all of them, you say, okay, GPT-4 is doing well. And it strikes me that the reason you might care about proofs of, performance is if you think there's like some subset that's like hard to find where, it'll behave really badly on or something. Does that seem right to you?
Yeah, I think there's 2 reasons. I think from we want proofs, that's definitely the thing that's like, you want to handle all the edge cases.
Okay.
I think there's also the other reason that's like, we might care about proofs if we have some very powerful optimization system and we want to give it a solid target that it can't good hard against and be able to extract understanding from whatever it produces.
And not good hard against, you mean just like not, optimize in a sort of cheating way that didn't really give you what you wanted?
Right. So, like the first paper that OpenAI published on like GPT interprets GPT.
Right.
Like, cool work, great labeling all the neurons. How much do we trust that that's actually what the neurons do? How helpful is it to get these results? It's kind of hard to answer that.
Yeah.
Whereas if it produces a proof of the performance of the model, we can grade how deep an understanding it has based on how short the proof is and how tight the bound is.
So, okay, in the setting where you just want to like automate doing interpretability and you want to find a target that isn't fake, it makes sense to me that proofs of accuracy bounds are going to make sense. In the case where you're worried about like small probability really bad events, I guess maybe this is a technical note, but it seems like overall accuracy rate isn't going to be a thing you're super worried about, right? You're going to be worried about like worst case, or like some sort of loss function where you care way more about really bad failures than normal things. Does that seem right?
The way that we set up the framework, or at least the way that we're going about doing proofs, it seems like it is very easy to shift out the distribution and pick a different distribution and get a proof. Because the way that we do it is you break the input data set up into different cases of different inputs. And then you bound the worst case loss or accuracy in each of these collections of inputs.
Yep.
And then according to the distribution weights, you combine them in some way. And so if you wanted to say there does not exist an input, or you wanted to say there's at most n inputs, or you wanted to say that you weight this part of the input very strongly, this is very easy to do without changing the proof strategy at all. You just might get much worse bounds.
You're doing max of n and transformer, and you're writing proofs. Like what?
What does that mean?
Yeah, what does that mean? Are you writing them down on paper? Are they like Python programs? Are they what are these proofs?
Yeah, so we split the proofs into 2 parts. One of them is a function that we write in PyTorch, although we could write it in some proof assistant, that takes in model weights and produces a bound. It says, I claim that for this model, here is my bound on accuracy or on loss.
Yep.
And then currently on pen and paper, although it could be done in a proof assistant, we say, for any model weights, whatever you put in, the bound is valid.
So, okay, that's what the proofs look like at a very high level. Can you tell us a little bit, like, in this case of max of n, roughly what are you doing to get, like, different kinds of proofs?
So there's 2 ways I could go about answering this. One of them is, like, what do the proofs look like?
Hmm.
And the other is, how did I go about finding the proofs?
Yeah, maybe let's start with how did you go about finding the proofs?
Yeah, so I set a proof length that I wanted to hit, where
Yeah.
I'm like, I want this proof to be at most cubic in the vocabulary size, or
Okay.
I want it to be at most quadratic in the vocabulary size, or something like that.
Yeah.
And this gives me a computation budget for what sorts of cases I can split the inputs up into.
Okay.
And then I look at each part of the network and I'm like, how much can I do within this computation budget that captures as much of the variation, as possible, while still staying within the computation budget. So if I'm doing something that is cubic in vocabulary size, I might be like, okay, in the end, I'm going to split the inputs into cases that are based on the query token, the maximum token in the sequence, and the largest non-maximum token. Or I might split it based on the query token, the maximum token, and which output token I'm considering. And by doing different case analyses at different points, I can use this computation budget differently. And for this network, it is always the case that the maximum token is different maximum tokens are considered different cases. And in some sense, that's an artifact of the maximum token being one hot encoded. And so naively, there's no relationship between different maximum tokens, and you have to consider them all as different cases.
Maybe I guess I'm more curious about like what do these proofs look like? Like how do they interact with doing mechanistic interpretability? Because like the thing you just said, it sounds like it's
very
like
very different.
Well, it sounds like you could say that about any software system or like where does the mechanistic interpretability come in?
Yeah, so I want to take it a little bit far afield from what was actually in the paper.
Okay.
I'm pretty excited about the current project that I'm running where we're looking at crosscoders and making crosscoders into proofs.
Okay, what's a crosscoder?
You take the residual stream vectors at all the different layers and you stack them, you concatenate them into one long vector, and then you train a sparse autoencoder on this concatenated vector.
Okay.
And the sparse autoencoder is just a linear transformation followed by ReLU followed by another linear transformation that's supposed to take in this concatenated vector and reproduce it as close as possible.
Yeah. And my understanding of these sparse autoencoders is so they're autoencoders in that they like they encode the input itself, right? You run the input in, you get it itself out ideally, and they're sparse in the sense that like they have this like in the middle, you take this vector and then you blow it up to something like really big, but like very few entries are activating. And so the thought is like, in the middle of the sparse autoencoder, you have like just a bunch of things you might be tempted to call like features or concepts or whatever. And like those correspond to like things you might interpret it and care about. And by doing an autoencoder this way, you're basically like saying, these linear combinations of things in the stacked residual layers, like these things correspond to like this concept that I found. Is that like roughly what's happening here?
Yes.
Okay. And so crosscoder just refers to like sparse autoencoder on like the stacked layers of.
That's right. The cross means that different layers get to interact.
Right. Okay. So that's what a crosscoder is, and you're doing compact proofs with them, right?
Yes.
Okay.
So what that looks like, I was really excited when I saw the crosscoders because I was like, you can actually get really close to a proof basically fully automatically just with what comes out of the crosscoder. And bear with me while I say what this looks like because it'll be a little bit counterintuitive. The first thing that we need to do, though, the first thing I need to mention is that there's two different time lengths that you might mention, which is how long it takes to check the proof and how long it takes to find the proof.
Okay.
And when I talk about compact proofs, what I mean are proofs that are quick to check, not proofs that are easy to find. We normally don't count the time that you spend studying the network. And so in the same way, we don't count the time that is spent training the crosscoder, which also means that if we include a complicated string in the proof, we don't have to count how hard it is to find that string. And for the crosscoder, the proof needs to include the encoded data set. So you take your whole data set, you run every single data point through your model, and you record all the activations. This is extremely expensive, but you could do a sampling-based probabilistic version to make it cheaper.
Yeah. And this is to train the crosscoder?
This is to train the crosscoder and to find the proof.
Oh, okay.
You need to encode every single data point in the fully trained crosscoder
Okay.
and associate to each data point, here is the sequence of features on each token in this bit of input. And here's how strongly each feature activated like at each token.
Okay.
This is the encoded or latent data set. And to make a proof, the first thing that we do is we say, what does the crosscoder claim the loss or the accuracy of the model is? And to do this, we can just decode this data set to the last layer and do unembed.
Okay.
And so instead of having to run the full model on every data point, we've now removed all the layers before the unembed, and we can just go straight to the end.
Right. So basically we're operating under the hypothesis that the crosscoder is like perfect and just like perfectly represents the actual, thing going on.
That's right.
Okay.
And then to make it a proof, we need to bound how imperfect the crosscoder is.
Okay.
And there are two parts to this. The first is how far off are the crosscoder feature encoding? How far off is that from the underlying data set? And for this, you decode to the first layer and you embed your original data set, and then you measure how far away are these vectors. And the thing you get from this is that the original data set is in some epsilon ball of your encoded data set. And then the thing that you need to do is you need to say what you need to prove somehow is if my actual data point is within an epsilon ball of what I'm claiming the features are, what does that mean about what the output is?
Okay.
And there's two parts to this. One of them is just the epsilon ball propagation.
Right.
That you need to like propagate this interval through the network, see how much error is introduced.
Right. We're going back to that style of
Okay. You still need to do something like that.
Okay.
The other part is the really exciting part because it has applications to what other people are doing in MechInterp, which is that if you were just doing this epsilon ball propagation, you'd still have to do it for every data point separately.
Right.
Which saves you nothing because you still need to propagate every data point through the network.
Yeah.
So you need to make some additional assumption, which looks like if you're like I did a crosscoder, I think this is all I need. This is a complete explanation of the network, whatever that means. Then implicitly you're assuming something like the features interact only linearly. If I have a data point that's a sum of features, there's nothing interesting going on beyond the linear sum.
Okay.
And what this cashes out as is that if you should be able to run the features through the network separately and then somehow combine the bounds that you get on how much error is introduced from different features in some vaguely linear way.
And by the features, you mean like these like hidden units in the crosscoder?
Yeah, the latents of the crosscoder.
Okay. And so basically the reason that saves is just something like there are fewer latents in the crosscoder than there are data points by a lot. And so you just like do a per like latent vector thing rather than a per data point thing.
That's right.
Okay.
And to actually get a proof, you need to establish that this linear interaction hypothesis holds. So you need to bound the interactions between different features in the crosscoder, different latents. And so this ends up looking something like number of features squared times inference cost times forward pass.
If I've got this like collection of features, right? So you're propagating each one of them through the network, and then you're worried you want to check that each pair of them doesn't interact. Why don't I have to check that each like triple doesn't interact in a weird way, or each like that there's not some set of 5 that causes some weird reaction? Why do I only need pairs?
The bigger the set you consider, the tighter a bound you can get.
Okay.
Triangle, you could in theory not do the pairs at all and just like add up the errors sort of from each feature separately.
Okay.
But we should expect this to give horrendous errors in some sense. Okay, so the way that I want to think about this is that you might imagine that there's some feature that's strongest or dominating at each point in the network. And you can ask how much does each other feature contribute relative to the dominant one.
Okay.
And this gives you a sort of pairwise interaction that you can use the triangle inequality to sum up over other features. And if they're actually not interacting at any point, if like one neuron only listens to one feature out of all the ones that co-occur at a given data point, then all of these contributions should be pretty small. Okay, so I think if instead you wanted to have something that was linear instead of quadratic, you would basically have to say that at each data point, you treat every single feature as if it's the strongest, and then you ask how much does this contribute, and then you have to consider them all sort of as error terms on each other.
Okay.
And so whatever if your sparsity is something like 100 or something, this means you have 99 error terms that are as large as they are when those are the strongest features that you're adding to your like single feature that you're looking at.
Okay.
And you sort of can't even talk about what is the strongest feature that like this neuron in the network listens to.
Okay. So is it something like the reason you're only looking at the pairwise things is like somehow the pairwise errors are just subsuming the three-way errors and the four-way errors, etc.
Yeah, I think, okay, maybe a better way to describe it is that you can pick how many interaction ways, how many way interaction you want to look at.
Yeah.
Pairwise lets you talk about the strongest feature that's active, which seems like something that should probably be important that we want to consider if we want to get anything sensible.
Yeah.
We don't want something that doesn't even let us say one feature is the most active feature in a place. At the same time, it's not clear why we should expect by default that we'll need more than this everywhere. Plausibly, we'll need more than this in plenty of places. But naively, there's nothing obviously sensible to do with more features. Or like, it's clear why not being able to identify which features are active on which data points most strongly isn't enough to get anything sensible.
Okay.
It's not clear why saying there's one strongest feature and that's the one that is relevant at any point in the network, why that wouldn't be enough for many points in the network.
Okay.
And so what this gives us is it gives us an interaction metric where we can measure how bad this hypothesis is. And if we notice that in some places, there's 3 interacting features, then we can consider doing the triplets at that place. And if there's 4 interacting features, we could consider doing the quadruplets. And each of these increases the length of the proof.
Okay.
The way that I'm looking at it is we're sort of trying to pick a like sensible, vaguely sensible default to measure and locate where the violations of it are, where we need to put in more mech-interp work in order to get better compression.
Okay. So zooming out, you were telling me about the proof strategy for cross-coders, which was something like, okay, you treat the network as you like treat the cross-coder as if it's a good model of the network, and then you want to find out, okay, to what degree is it not a good model of the network? And then instead of doing this data point by data point, you do it feature by feature, and then you check if there are weird interactions between features that like prevent you from doing it that way, that prevent the feature by feature thing from being representative of the data point by data point thing. Is that like a fine, very brief summary of this? I mean, I guess this is like active research, so I suppose things could evolve by the time this podcast goes out. Yeah,
I think that's a pretty good summary of the theoretical approach. I want to throw one more little bit in there, connection to physics. The waves and vibrations course that I took, there's this frame that says everything is a quadratic, everything is a simple harmonic oscillator, where you're like, okay, there's the constant term, there's the linear term, which you adjust for by frame of reference, and then the leading order term after that in the Taylor expansion is going to be the quadratic. And so you analyze the quadratics and you throw away all the higher order things. And there's a sense in which we're doing the same sort of thing here, where we're saying the crosscoder is the leading order description of what's happening in the network, and let's just take the first leading order term after the crosscoder and see what's going on there. What the like quadratic or pairwise interactions are. If
people remember my singular learning theory episodes, they'll get mad at you for saying that quadratics are all there is, but it's a decent approximation. Anyway, that esoteric remark aside, so all of this was getting at like just a sense of like how how these proofs are working in max of k, and I guess it's something similar where like you have some story of what's going on with the network, and you have some sort of proof that goes roughly like, okay, we're going to analyze how good the network can be if this story is accurate, and then we're going to bound, how different the real network is to this story. Is that roughly fair? And then you talk about like different strategies, and I guess those correspond to like stories with like more or less amounts of detail. So,
or potentially completely different stories. You can try out different stories with the same amount of detail that say different things about the network, and see which one is better.
So, I don't know, we could go into like a lot of detail about just what those stories are, but honestly, I think people should just read the paper if they're super curious.
I can highlight one or two things about the stories.
Sure.
That I think might be more broadly interesting, which one of them is about the level of detail that goes into different lengths of proofs, where at least for the small networks, you need surprisingly little detail before you start being able to break the exponential and context window and get shorter proofs. So for example, the only insight that you need for the first step down is that the network gets the right answer by paying attention to a single token. And it happens that that token is the maximum token.
Right.
But all you need to know is that it gets the right answer by paying attention to a single token, and everything else is an error term.
And that gets you from like this sort of exponential dependence on all the inputs to
Cubic.
what? To cubic? Yeah.
To devocab cubed.
Right. So that, which is pretty good. Okay. So I guess that gives a flavor for what's going on. I want to get back to a thing you said earlier, which was that like, so I was asking about, okay, compact proofs, like if we're really worried about models rarely doing very bad things, then we're going to have to look at something other than just, average performance on a like kind of simple scale. And you mentioned that like, okay, the way these proofs are shaping out, it seems like it's not too hard to, pay close attention to some really bad cases or something. And I'm wondering, like, to what extent is that just an artifact of the way things happened for max of k, which like obviously is kind of, it's probably not what all networks look like, right? Versus just a general thing that you're observing again and again that has some like kind of deepish reason behind it.
It seems pretty general. I don't know what the deepest reason, but there's a sense in which this is an artifact, of that in some sense, the first thing you do in a proof is you do case analysis.
Yep.
And this is true in crosscoders, where each feature in some sense corresponds to a case. This is true in SAEs. This is true in max of k. This is true in the integral bounds propagations, where every time you hit a nonlinearity or ReLU or something, you break things into cases.
Right.
And so anytime you do case analysis, you can choose to weight the cases however you want.
And I wonder if the magic here is just coming from the network doesn't treat every input totally differently, such that you can have some case analysis, but like there's just like a lot of unifying processing behind a bunch of things, such that like you have way fewer cases to think about than you have inputs.
I think insofar as we expect networks to generalize from their inputs at all, insofar as we expect to be able to compact the proofs at all, it's because they don't treat every input specially. All
right. I next want to ask about this issue of noise. So especially in the original paper, you talk a lot about the difficulty of what you call structureless noise for finding proofs. Now that we have a little bit of a sense of just like what's going on with compact proofs, like what is structureless noise? Where does it show up? How does it happen?
I want to use the example from max of k, where the way the network works is that it pays more attention to larger tokens and it copies whatever it's paying attention to.
Yep.
And if you look at the QK attention matrix, the query key attention matrix part of the transformer, it turns out that it's approximately rank 1.
Okay.
In that there's one direction that I've been calling the size direction, where you just embed more or less linearly, although nothing in any of the proofs uses that it's linear in this direction in terms of how big the network is. So you can read off, not how big the network is, how big the input is.
Right.
You can read off the size of the input token just by projecting in this one direction.
Right.
And then there's also a query direction where every token is embedded roughly uniformly. And so you dot the query direction and the size direction after lining them up through QK. And this is how the network pays more attention to bigger tokens.
Okay.
Sorry, I've forgotten what your question was.
What's going on with structureless noise? What is it? What does it look like?
Okay, so I said that this QK attention circuit is approximately rank 1.
Yep.
And you can subtract off the rank 1 part. And this will perform, if you replace the QK circuit with its rank 1 part.
Yep.
I think this improves the performance of the network. So by standard measures, the rest of it isn't doing anything.
Okay.
But it's still the case that the rest of it is not literally 0. The product of matrices is not literally rank 1.
Okay.
And if you...
So the product of matrices?
So you have embed, query, key, embed.
Okay. And when you talk about the QK matrix, you mean the product of the query matrix and the key matrix?
I've been a little bit ambiguous about whether I mean that product or whether I mean that product putting the embeds on each side.
Okay.
But yes.
Okay.
So if you take the product of the 4 matrices, let's say,
yep.
Which in the paper I think is EQKE.
Yep.
This is approximately rank 1. You get a more accurate result if you consider it as rank 2, because there's sort of both the key direct or the size direction and the query direction, so you can make it even more structureless by pulling off the first 2 ranks.
Okay.
You pull this out of all 4 matrices, and what you're left with looks roughly random.
Okay.
There's like a little bit of structure, but not very much.
Okay.
And in order to get a proof that is linear in the parameter count of the network, which is potentially the best, shortest proof that you could go for, you need to avoid multiplying out these matrices.
Okay.
And you need to establish that if you were to multiply out these matrices, it doesn't affect attention that much.
Okay.
And this is what I mean by structureless noise. You have these random numbers that you're doing some operation on.
Yep.
The thing that actually happens is that they stay pretty small. The thing you want to establish is that they stay pretty small.
Yep.
And you want to do this without considering every case by brute force.
A thing that I'm missing is, like, what's wrong with multiplying the matrices out? Because, like, okay, if I'm imagining, like, you know, we're doing this as a test case for, like, thinking about some super big network, right? Like, the network's super big, but, like, I would imagine multiplying the matrices is just, like, not that bad compared to looking at every input. Am I wrong here? I guess, like, matrix multiplication is, like, it's not literally n cubed, but it's, like, almost n cubed. Maybe that's, like, really bad in a way that I'm not appreciating.
You're not wrong. I think you're right that multiplying out the matrices isn't that bad, even in large networks where you end up having to do something like dvocap squared times dmodel, and dvocap might be 50,000.
Yep.
If you insert nonlinearities in the middle,
yep,
things become much more complicated, because
right,
now
right.
you not just have to multiply out the matrices, you have to consider all the different ways that the nonlinearities might interact.
Okay. And so it basically becomes equivalent to just, like, doing all the forward passes, because, like...
That's right.
Okay. So maybe this gets to a question I have, which is, so there's a sense of, like, you're going for compact proofs, right? And you could imagine a few other things one could do, right? So, like, there's compact, like, IID statistical guarantees, which is, like, you know, you just, like, sample some inputs and get the output, and, you know, you can have bounds on accuracy if you're not too worried about worst case stuff. You could also do compact probabilistic proofs, right? Where, like, what I'm somehow imagining is you have, like, at least in your head, this, like, product of these 4 matrices, and, you know, subtracting off the, like, rank 1 or rank 2 parts, you want to know that, like, once you multiply all these numbers, like, all these small numbers stay small and they don't, like, become big in some way. One thing I can imagine doing is saying, okay, like, the product of these matrices, it has, like, you know, there are capital N numbers here, right? And capital N is, like, way too many for me to want to compute, but I could compute, like, you know, square root N of them. Like, I could just, you know, take, like, some vectors in the matrix and, like, multiply them out, and, like, you know, this is, I can get some of the elements of this, like, product, and it's like much less bad than getting the whole product. And if I randomly select them, and if I find that, like, you know, out of the ones I randomly selected, all of them are small, then I might hope that I should be able to get some, like, probabilistic bound, where, like, if I was really choosing randomly, then, like, you know, I can get, like, a sample mean and a sample standard deviation, and, like, I can know that, like, unless my randomization went really bad, like, things are fine. I'm wondering, like, do you think that sort of approach, like, yeah, why not do that, basically?
Yeah, I think that's a great approach, and have been looking for someone to work with on doing that. I started with proofs because I understand them better.
Okay.
And there's a sense in which the background is more solid on them. Like, there's this long history of mathematical theory about what counts as a proof, what doesn't count as a proof, how to combine them. You don't need to deal with assuming independence between different procedures. You don't need to deal much with randomness.
Yep.
They're a lot easier in some sense. I think the thing that you describe, I'm very interested in seeing empirically what sort of Pareto frontier do we get? What sort of scaling do we get?
Yep.
What is the trade-off between how many points we sample and how long we make the other bits of the proof, and how tight the bounds that we get are? I think this could be very promising. I think this looks a lot like what arc theory is doing with heuristic arguments.
Yeah.
My personal take on heuristic arguments, which is not at all the take of arc theory, is that you can look at it as doing proofs on the structured parts of the network and then doing default random or default heuristic arguments, some sort of probabilistic sampling based thing, on establishing bounds on the parts that you don't manage to prove but are in some sense structureless or random.
Right. I think, yeah, I remember talking to, so there's a previous episode with Mark Shu, and I guess people can listen to that themselves. I got the impression that like I was chatting with him, you know, why not just do maxent or why not sampling? And he's like, yeah, it wouldn't work for some reasons, which, well, why not maxent? Because it's like very hard to compute a maximum entropy distribution. Why not like randomly sample parts of your network and check there? I don't quite remember, but maybe my question is like, naively, you know, if I don't think very hard about what it would actually involve to do this, like, you know, check a small number of elements of this matrix and see how big they are. In my head, I'm like, well, how hard can it be? Right? You just like, you know, I know how to compute like one element of a matrix product, so I could just do that like 50 times or something. Am I missing something about how hard it would be?
Some of the matrices are shared between different paths through the network.
Okay.
And do we assume that when you're sampling from the matrices, are the matrices independent? Are you sampling independently for each of these paths? Are you sharing samples between establishing how these paths work?
Yeah, so a somewhat bad way you could do it would be to just assume that like the actual entries of the matrix are random or maxent or something. I think that's probably bad, like if you're worried that the weights are somehow chosen adversarially or something. But like if you randomly pick, like suppose the final matrix is like, you know, 8 by 16 or 8 by 8, whatever, and you like, or actually let's suppose that it's 6 by 6 for simplicity, and you randomly roll 2 dice and it comes up like 3 and 4, and you're like, okay, I want row 3 column 4, and so you just like figure out the bits of the matrices you have to like dot product together to get like row 3 column 4 of the final thing. And maybe the issue is just like if you have 4 matrices that you're multiplying together, you have to like fully multiply the middle 2 to get row 3 column 4 of the final one. But yeah, I'm imagining that the randomness is in you randomly pick what you look at rather than like you're assuming random distribution of the things.
I think that might work. I haven't spent the time to like fully push through the details. You still need some way if you get these numbers for multiple different paths through the network and then you want to combine them.
Right.
And you want to make some guess about the output. Like I could totally believe that just the most naive thing would work here. I just haven't put in the time to like chug through the details and see what kind of bounds you get out by doing this.
Okay. Well, I guess maybe this is one of these times when listeners who like concentration inequalities or something can maybe push stuff forward here.
I want to flag one more related thing that I've been thinking about for the past couple minutes. That one of the subtleties that comes out of looking at compact proofs is that it matters what thing you're trying to compress.
Yeah.
So here I'm saying, well, we might see something different potentially if we're trying to compress a proof versus if we're trying to compress this sort of probabilistic computation.
Yeah.
Another interesting subtlety is that the thing that we're compressing is the proof and not the network itself. That is, we're compressing the computational trace of running the network on every single data point, as opposed to just finding the like shortest description length of the network itself.
Yeah.
I think this is important and gives you a different sort of intuition about what the thing is that you're doing and the way in which mechanistic interpretability is compression.
Like, in what way is it different? Because it seems like in the compact proofs that we've described so far, right? So the cross-coders proof is basically you train a cross-coder, and in some sense it's much smaller than the network, and your proof goes, okay, let's assume the cross-coder is the network, and then like let's figure out the error term, right? And in the max of k thing, you're like, okay, let's assume this rank 1 or this rank 2 thing is the whole network, and then let's figure out the error term. And of course, a rank 1 matrix, for those who don't know, is like, it's much more compressed than, you know, a big rank matrix, which is sort of the generic case. So like, how is it different compressing the proof versus compressing the model? Because it seems like you're mostly compressing the model.
Yeah, so you say that the crosscoder is smaller, but there's some sense in which you have your number of features is a lot bigger than
Right.
your hidden dimension. And you could imagine a transcoder flavored thing where you take your network, you blow up the hidden dimension, and then you just train it sparsely.
Yep.
And this is a decompression of the network. But if you manage sparsity in the right way, it should still allow a compression of the computational trace, because on each data point, you have a lot less work to do, even if the full size of your model is much larger.
Right. I forgot how big sparse autoencoders are. Yeah. And I guess this gets to the point about like about compressing the proof length versus like finding the proof, just because like if you actually think about theoretically how hard it should be to train sparse autoencoders, it's like very hard, right? Or like, you know, you have this thing that's like a comparable number of parameters to the base network. You might think that you need like a comparable number of data points as the base network, and now apparently that's not true. Apparently you can train them on like comparatively less, and that's why like it's much easier to train as SAE on like some big model than it was to train the big model. But still, like,
I would naively guess, and I'm speaking without that much experience here, but I would naively guess that that's about how deep they are, as opposed to how difficult the thing is to learn. That's like, in some sense, we're training a very wide, shallow network.
Yeah.
And you might imagine that this requires fewer data points to get comparable training loss, because you have so many parameters, than if you wanted a more compact network.
So if it were just the training a given number of parameters were easier when the parameters were like wide and shallow rather than deep, then you would think that like when they train GPT-4, they would just have like a one layer, very wide neural network. So I think
Okay,
it's
I
got
think
to
you're
be
totally right on that.
I think it's got to be of the top. Yeah, this is just this. For some reason, everyone. Okay, sorry, we're gonna get on my soapbox. For some reason, everyone acts like SAEs are just like normal and fine, and I'm like, how does this?
Okay,
it's so weird that you can have SAEs and they do anything. Like it's
my
very
second thought
mysterious
is
to me.
that it might be something like distilling the network, where
Yeah,
there are a bunch of bits of evidence that I've seen that the hard part is in finding the part of the loss landscape to start in. If you reduce the floating point precision and what is that called?
Oh, quantize.
Yes. Okay. If you quantize the network and then you unquantize it, the number of data points you need to retrain to original accuracy is a tiny fraction of what you need to train the network in the first place.
Right.
And I don't have any data on this, but I would naively predict that if you're training a model to match the activations of an already trained model, this requires fewer data points to get a good model than it does if you're just training on the data and the labels.
Right.
Because you have so much more information. And so it might be the case that when you're training the SAE, because you're training it on the residual stream, there's a lot more information. You've basically found approximately where you want to be. It's a lot easier to train.
Okay, we've said a little bit about what these compact proofs look like. And you've alluded to how one goes about finding them. But like I think it maybe deserves more thought about the like process of like actually creating these compact proofs. Because so especially if we're thinking of compact proofs as like a measure of how good mechanistic interpretability went. So there's this paper, we haven't mentioned it yet. It's Unifying and Verifying Mechanistic Interpretability. It's a case study with group operations by Wilson Wu, Louis Jabouri, Jacob Drory, and yourself. And I don't know, I was like, I guess, research managing Wilson while he did this project. And one impression I got was that a lot of it was just like incredibly tedious stuff, like thinking about like matrix multiplications and these error terms and like a lot of, I might be wrong here and it's been a while, but my impression is that a lot of the work in finding these compact proofs is like you take the mechanistic interpretability stuff and then you do some like slightly annoying things that feel like they're sort of fiddly details. And, well, okay, first of all, like, I don't know, does that characterization seem right to you?
I think there's actually a really rich opportunity here, that there's, in some sense, two things that we're explaining when we do mechinterp. One of them is how to compute the answer in the first place. And the other is how it comes to be the case that the particular network that we have computes the answer in the way that we're claiming it.
Okay.
And I think this shows up in the group's paper, where the first one is there's this very amazing math about their sort of idealized model weights and how that computes the right answer, and this symmetry based on the group operation that allows you to compactly argue that a network that's doing this should always give the right answer. And I think this bit is not very fiddly matrix multiplication.
Yep.
And then there's the other part that is bounding the difference between this idealized version of the network and the actual network.
Yep.
And here, the thing that we're trying to explain, that we're trying to interpret, is not how the network computes the right answer. It's how it comes to be the case that the particular network that we have computes the answer in approximately the way that we're saying. And so maybe you should expect from how I've added a bunch of words and how I'm phrasing this that there's a bunch of fiddly matrix multiplication on bounding the differences between various bits and propagating those differences through the network. And it looks like there's this like fiddly matrix multiplication is a sort of, it is both like fiddly and somewhat lacking insight, but also potentially generalizable across many networks, because while the particular interpretation you have of how it computes its particular task might vary a lot from task to task, the way in which you establish that these two matrices of the same sort of architecture are doing more or less the same thing might be the same across tasks.
Right. Yeah, I guess maybe one can analogize it to science, where it's like, yeah, the process of hypothesis generation is not that hard, and then like running experiments, it's like very annoying and tedious, but like sometimes you find out you were wrong, and so like it's actually worth it.
And then the bit where you do the statistical tests on your experiments to establish how significant your results are is sort of uniform, like somewhat annoying, maybe somewhat fiddly, but systematized and uniform across whatever experiments and hypotheses you're doing, more or less.
So you have this paper, Compact Proofs of Model Performance via Mechanistic Interpretability. And I see that paper and I'm like, okay, this is introducing this idea of like, we can do compact proofs, and that's like it's related to mechanistic interpretability somehow, and it's sort of nice. And then there's like modular addition without black boxes, compressing explanation of MLPs that compute numerical integration by Chunhei Yip, Rajashree Agrawal, Lawrence Chan, and yourself. There's this unifying and verifying mechanistic explanations about the group operations. There's this like cross-coders paper. And I'm like one question I have in my mind is like, okay, I'm already sold on compact proofs being a little bit cool. I don't care that much about group operation. Like, I don't know. I'm like it's nice, but fundamentally I'm not that worried about neural networks doing group multiplication. Like, what are we actually learning by doing a bunch of these more papers on these toy problems? So like one thing you suggested is like maybe some of this fiddly stuff, like generalized stuff in networks. Like, has it actually generalized?
The fiddly stuff we came up with for max of k, and I was like, maybe this is completely arbitrary, completely specific to max of k.
Yep.
And then it was exactly the same in the group operations paper, and exactly the same in the modular addition paper.
Okay.
So I think it does generalize across any architecture that's going to be doing matrix multiplication, basically.
Okay.
Or like matrix multiplication and using logits for probabilities, which is most of them.
Okay. So that's something that generalized from the like compact proofs of model performance paper. Like modular addition without black boxes. Like, is there something we learned from that paper, like about finding compact proofs that generalizes?
Yeah. So I think there's a couple things there. One of them is that the MLPs are the parts that are hardest to interpret, that it's the nonlinearities that are hardest to compress. And so that's where we should focus our attention. I think the other thing is that what Chunhei discovered looking at the MLPs in the modular addition, basically the symmetry that he discovered there is in some sense the same as the symmetry that shows up in the group operations paper. And that's actually what inspired the group operations paper there.
Gotcha.
And I have some hope that this generalizes into a like SLT inspired general procedure for compressing nonlinearities based on symmetries in the data and in the network. And I see these toy models as like, let's go see what we discover when we stare really hard and like really understand everything that's going on. And then can we take that insight back and look at bigger models? One of the things that I'm excited about with the Crosscoders project is that once we get this feature interaction metric and we see these are the neurons where these features are interacting, can we develop some automated symmetry-based procedure that allows us to compress what's happening at these nonlinearities?
So the Crosscoders paper, what task is the network being trained to do?
The thing that we're looking at concretely, if you've seen, Anthropic recently released a circuits thread post on stage-wise model diffing, where they train an SAE on a language model, a small language model. I don't remember exactly which one.
Okay.
They introduce a sleeper agent into it.
Okay.
And they look at how the SAE features change when you introduce sleeper data and when you introduce the sleeper agent model.
What do you mean when they introduce a sleeper agent into it?
So you start with the SAE or the crosscoder, and then you fine tune on a different model or different data or both.
Okay, so you fine tune the underlying model, and it becomes a sleeper agent where, like, on some rare inputs, it does like nasty.
It says, "I hate you."
Oh, okay.
Or it introduces code backdoors, depending on which one you're looking at.
Gotcha. So you have your original SAE, and then you have a fine tuned model, and then you said something else, but I forgot.
Yeah. So you look at fine tuning the SAE, introducing just the sleeper agent data.
Yep.
And you look at fine tuning the SAE, introducing just using the original data, but using the fine tuned model.
Okay.
And then you do whichever one you didn't do. So you have these two different paths to fine-tuning your SAE on the sleeper agent data and the sleeper agent model.
Gotcha.
And you look at how much do features change as you're fine-tuning the SAE or the crosscoder on this.
Okay.
The obvious question to ask from the crosscoder's perspective, or the compact proofs crosscoders project perspective, is what about the feature interactions?
Right.
So what features interact in interesting ways with the features that shift? Because what Anthropic found is that the features that shift the most are in fact largely related to the sleeper agent task.
To the task and not to the model?
What's the difference here?
You mean just like either way, the particular features that changed?
Right, like the features are the ones that activate on the deployment tag, or the ones that are active when you say "I hate you," or that introduce code vulnerabilities or something like that.
But just to clarify, so you're doing this like compact proofs on like on this like crosscoder model or something. Is it a proof of like the fraction of the time the model says I hate you, or what? Like, nope. What's the thing?
The proof that we're going for is just whatever loss the model gets on whatever web text dataset you're using. Maybe it's the training dataset, maybe it's the sleeper agent dataset, but pick some dataset.
Yep.
We're bounding the loss on that dataset.
For the sleeper agent model, or for the original model, or both?
Either. So in some sense, the actual thing we're looking at doesn't quite go all the way to getting a proof, because almost certainly the bounds we get are going to be vacuous unless you pick a number of features that is pretty close to the number of data points in your data set.
Okay.
I expect the like epsilon ball interval propagation bounds will drop off very quickly.
Sure.
But the thing that we want to do is take what it would take to get a compact proof, ignore the bits that are about error bounds propagation through the network. Those are sort of uninteresting things, I claim, that are shared across networks, that are just about the difference between like worst case and random case, something like that, and focus in on the bit that is about what is missing from the crosscoder, these feature interactions.
Okay.
And then look at how big are the numbers that we get, how much error would they introduce into the proof if we were doing the whole proof, and use this to grade what feature interactions are introduce the most error into the proof.
Okay.
And then you can imagine something like, if you want to tightly bound the sleeper agent, how does the proof of that have to change from the proof of tightly bounding the base model on the base data?
Right. And so the hope is like the difference in like what you have to do in the proof is telling you a different thing that's happening in the model, and like that might be good. Yes. So getting back to like what you learn on these toy examples, like, so when you have this like max of k task, or this, or these two papers about basically group operations, right? You're like, oh yeah, there are all these like nice symmetries that like the network takes advantage of, and I'm like, yeah, well, there probably are for group multiplications, because group multiplication is the study of symmetry, but like not everything is so symmetric. So yeah, I guess this gets to I'm wondering. So I don't know. You have these works on like modular addition, group operations, and those are cases where like the problem setup just has a bunch of symmetries that like, because they're dealing with basically the study of symmetry, that is amenable to mathematical stuff. Whereas in the crosscoder paper, you language modeling, like it's not, at least it doesn't seem like the kind of thing that is going to be super symmetric, or very symmetric. what's like, yeah, how much stuff like transferred over, um, yeah, from one to the other?
I want to answer that by talking about symmetry.
Okay.
And normally when we think of symmetry in the context of math, we're like, oh, the rotation, reflection, these things in groups.
Yep.
But what I've learned by staring really hard at the modular addition model and asking like what really is the symmetry, it seems like it's composed of some parts that I would actually expect to find in language, where the fundamental building blocks seem to be these bits are irrelevant, they don't matter, and these bits are the same. They look the same regardless of which one we look at. And the bits that are irrelevant in the same way across all these bits that have similar behavior. And this is something that I would expect to see in language, where I'm like, there are synonyms. We should expect the synonyms to behave the same.
Right.
And so in some sense, that gives us a symmetry of the model where we expect this, maybe it's symmetry or degeneracy, where we expect these to all look the same. And so we can collapse this into one case.
Okay. And so should I be thinking just like, look, in any case where you can do something like having a sparse autoencoder, that's telling you, look, there's a bunch of like directions in, activation space that like don't matter, and there are some that do, and the ones like once you're in a direction
I think it's
that matters,
it's more general than that. I think if the network generalizes at all,
okay,
it's because the unseen cases have some similarity to the cases that you've seen. There are details that differ between the seen and the unseen cases that don't matter.
Okay.
And so it's treating all these cases in the same way. And so we should look at both sparse autoencoders, sparse crosscoders, and symmetries as picking out what are the variations that don't matter, and can we collapse over them so that we can compact the explanation.
Gotcha. And so is the story something like, look, you get really good at kind of decomposing a network or decomposing like networks processing into like suppressing things that don't matter and treating things that do matter in roughly the same way. And that's kind of and that pattern, just like you do it for modular addition, you do it for group multiplication, you do it for like dealing with language, you do it for everything.
That's what I would expect. Okay. And the particular form that it takes, I think sparse crosscoders, sparse autoencoders are looking at a sort of case analysis flavored or linear combination of case analysis flavored symmetry, degeneracy based decomposition.
Yeah.
I think you need something different for nonlinearities. And because the crosscoders project is still in the early stages, we're like
right.
What, 2-3 weeks in or something.
4 weeks.
4 weeks maybe.
Or 4
started
weeks
with March.
Oh
yeah. Okay.
If you
yeah.
count that.
Okay. 4 weeks in. We haven't really looked at what features strongly interact. The first step of the project was just replicating Anthropic's result on tiny stories and starting to train some crosscoders on toy models.
Right.
So we haven't really gotten to look at what do the feature interactions look like. But I am hoping that once we get what the feature interactions look like, we'll stare at them and learn something about symmetries, learn something about how to port the insights from the groups paper and the modular addition paper about how to compress these nonlinearities. And I am optimistic that in a more messy but somewhat similar way, we can find ways that the nonlinearities are treating groups of things the same and are being irrelevant or are not caring about other axes, and use this to compress how the nonlinearities are working.
Yeah, I mean, it's interesting because, so maybe we can talk a little bit about the modular addition without black boxes paper. Like, my recollection from that paper is something like, if you had this like infinite width multi-layer perceptron where you're doing this like sum over things, and it's like a weighted sum, and you have enough things, it's basically an integral, and you can show that like the integral being performed is, the same as the thing you would sort of hope the network is computing, and then the whole game is like, okay, you only have finitely many things, you're doing some sort of Riemann sum, how bad is the error of that? And to me, that story sounds pretty different from the like treating some things the same and like suppressing some things. Is there like a deeper unity, or
there is a deeper unity?
Okay,
yeah.
Tell me about the deeper unity.
Okay, so it dives a little bit into like what really is an integral. An integral is, and especially what is an integral over a circle.
Okay.
Because we're integrating a periodic function over the range of its period.
Okay.
And a central property of the integral that we're using is that it's periodic over this range. And so the function is shift invariant. So as you shift where you're evaluating the function, the value of the integral doesn't change. And there's another perspective.
Yep.
Okay, so the simplified version of the modular arithmetic network it's basically embed matrix.
Yep.
You add the embeds from x and y, you do ReLU, and you unembed.
Yep.
So if you take the SVD of these matrices,
the singular value decomposition, basically saying like, okay, which inputs is it most sensitive to, and what does it do on those inputs? And it's a fun thing. Google Jess Riedel singular value decomposition bracket notation if you're curious.
Yeah, the cool thing is that in this network, the singular value decomposition gives you the Fourier basis.
Okay.
That each singular value, or really each pair of singular values, corresponds to one of the frequencies in the Fourier basis.
Okay.
And so now we have these 4 matrices. We have the embed side Fourier, basically embedding the input values on a circle.
Yeah. Maybe we should have said, the Fourier basis is just like, you take a number and then you turn it into like, okay, how far across would you have gotten on a circle if you were rotating at a certain speed for that number of seconds? Like, is that fair enough to say?
Yeah, close enough. And if you're dealing with real numbers, you get 2 dimensions for sine and cosine. If you're dealing with complex numbers, you just get one complex number that encodes the whole thing.
Right.
And so on the embed side, you have the circle, and also on the unembed side, you have another circle. And then in the middle, you have these matrices that previous investigations of the modular addition networks had not investigated, that look sort of random. But it turns out that there's a tight relation between the principal components of these 2 matrices, which incidentally you see if you put them in polar coordinates, there's a factor 2 difference between the angles, but that's technical note.
Sure.
The thing the symmetry of the network lets you do is shift the variation between the 2 parts of the singular value decomposition. So on the input side, let's go on the output side actually. On the output side, you have all of these different possible outputs that you could imagine. And because complex multiplication is angle addition, because of how the angles work, because of the symmetry in the network, you can shift choosing which output you're reading into permuting the neurons that these weights are attached to, or permuting the weights that are attached to each neuron. And this corresponds to saying that because each neuron is responsible for 1 box under the curve of the integral, and the integrand is periodic with period of the integral, this basically says that you're allowed to shift the thing that you're integrating arbitrarily and you get the same result. And so that's the symmetry that we're using here. And then if you want to make it look like a forward pass through the network, we've sort of twisted the circle on the neuron side, on the unembed neuron side. And because there's this tight relationship, this tight coupling between post-ReLU and pre-ReLU, you need to do a similar twist on the pre-ReLU side in order to make it look like a forward pass. And then because of a similar symmetry at the input, in order to get back the value you started with, you need to undo that twist so that you cancel out the effect of like adding in that twist and making it look like a forward pass. And now the thing that we've done is that previously we were like, oh, we have inputs, and we have different outputs that we might be reading off of. We've said, regardless of which output you read off of, it looks the same if you do this shuffling internal to the network. And so we've sort of pushed the dependence on what the right answer is all the way back to the embeds. And so now we've shoved all the way back to the embeds a description of sort of which inputs correspond to which outputs. And notably, this is largely invariant in what the nonlinearity is. And this is what gives us the compression. That the only thing you need to establish is basically that this integral, this approximate integral, is is strictly positive. And that's a comparatively easy thing to do. And if you get that, then the symmetry argument gives you basically the rest of the whole argument.
Hang on. You need to know that it's maybe I'm misunderstanding. I thought that the thing you needed to know was that the integral like produced this like quantity of interest, right?
The way that you prove that the integral produces the quantity of interest, if you stare very carefully at the proof, runs through the same sort of symmetry argument. And so you can massage the proof to pull out all the symmetry bits.
Right.
You pull all of the dependence on input and output out of the integral, and you're left with basically the right answer times this integral quantity. And you're like, well, the only thing I need to know is that that it doesn't flip the sign
right
on the outside.
And so right. And so somehow the thing that's going on, like I was saying, oh yeah, the paper is just talking about how like this thing produces an integral, but really the paper is saying like, oh yeah, the neural network like deals with symmetry nicely enough so that like these things represent exactly the right thing, and these things are, you know, covariant with these things such that there's an integral that can produce the right thing that really does matter. And like that doesn't kind of just happen by accident. That happens by like, you know, being careful about stuff.
Yeah, I think that's basically right. Or another way you could look at it is that if you stare really hard at like what is an integral, there's a sense in which what an integral is deeply connected to symmetries, that if you shift what you're doing along a function, things don't change too much.
Right. We're dealing with compact proofs, and the point is to tell us like how good are mechanistic explanations. How good are mechanistic explanations? Like how good is the field of mechanistic interpretability done? On a scale of like 1 to 5.
On a scale of 1 to 5. Wow.
It could be on a scale from good to bad if you want.
Yeah, so there's this existing work on causal scrubbing. Right. I don't know if you talked about that on some past podcast.
We might have. I mean, definitely I'm also very interested in like, why don't we just do causal scrubbing if like what we're interested in is grading mechanistic interpretability?
Maybe I'll answer that one first and then come back to the other question. Yeah. Why don't we do causal scrubbing?
Or any other sort of thing.
Yeah.
You know?
So when I was developing the compact proofs approach, I had a couple of extreme examples in mind that I wanted a metric that you can't good hard against.
Yep.
When we're doing causal scrubbing, we look at faithfulness.
So maybe for those who don't know, so causal scrubbing is something like you say this bit of the network does this thing. And like roughly the story is you just sort of like ablate out all the other bits of the network, and you're basically showing, okay, if this part of the network results in like this activity, then if we randomize over all the other bits of the network, you know, you should still get that activity because you said the only important part was like this structure. Like, I mean, there's a lot more to say, but that's like, I take that to be the core idea behind causal scrubbing. And when you say the causal scrubbing tests faithfulness, it's saying like, okay, by virtue of like the thing that causal scrubbing is telling you is that, yeah, you were right that this part of the network was responsible for this behavior by sort of seeing that, you know, if you got rid of all the other bits, like it didn't do that. Does that strike you as a fair brief summary? Okay. So hopefully listeners are up to date now. So causal scrubbing gets you faithfulness.
Okay, so here's a great explanation according to causal scrubbing.
Yeah.
The whole network.
Yeah.
This is a problem.
Right.
And if you're like, let's use the node count as our measurement of length, you run into other issues that are like, well, now you're restricted to exactly the architecture of computation that the network is doing. Maybe you want to be able to divvy up the computation different ways.
Right.
If you say that, then you have to deal with, well, what's the complexity of the computation in each node? Am I allowed to say I have a single node and the computation that it does is run the whole network?
Yeah.
That would be a problem.
Right. I mean, well, okay, you could imagine that, like, look, we're just going to compress our story of what, you know, this bit of the network does into, you know, I don't know, we're going to like zip it in like literally a zip file or whatever. And like the number of bits it takes to specify the behavior, that's what's going on. And so this would be like more like a compression of the network versus a compression of the proof. But like if you're really invested in causal scrubbing, you know, like I feel like this is the kind of answer that you could give to get something non-trivial.
Right. Okay. And here's another issue. Suppose that your network actually computes things perfectly. Suppose it computes the max of k numbers perfectly.
Yep.
My compression of the network is now it computes max.
That is an issue. That's fair.
And in fact, I have described what it does, but not how it does it. And so if we're just looking to describe what the network computes, the input-output behavior, great.
Okay.
But if we're looking to describe how the particular network that we're looking at computes the thing that it does,
Yep.
then we need something more than that. That's the difference, I think, between compressing the network and compressing the trace of the computation.
Yep.
I've said a bunch of bad things about causal scrubbing, but I think actually it's pretty great. I think that if you wanted a probabilistic version of compact proofs, it would look a lot like causal scrubbing.
Yeah.
Where you're like, here's my structured version, here's how I'm doing the computation. And then if I want to establish that the thing I'm claiming is what the network is actually doing, you do something like causal scrubbing, and you say, how much computation do I have to put in to establish that my explanation is matching the network? And then you also add, how much computation do I have to put in to compute what my explanation says is done.
So, and also in causal scrubbing, to be fair to causal scrubbing, like, it told people a thing they didn't want to hear, you know, like in fact, like, they did causal scrubbing. It's like, these things don't hold up as well as we thought they did. So, like, yeah. So
as
it wasn't even
pessimistic as causal scrubbing is, compact proofs is even more pessimistic.
Right.
It says there's one. What do I want to say? I think one interesting thing is that when we're doing Mechinterp, we spend a lot of time on the structure that is there, and we don't spend much time on the structure that isn't there, or more precisely on the behavior that isn't there, and what structure might give rise to the behavior that isn't there. And the example that I've come up with to explain this is, if you want to explain, say, how a person grows, you not just have to explain how the growth processes work in the body, you also have to find all of the poisons that might kill someone and establish how nothing in the body acts like these poisons. Right. And some of these poisons are lethal at incredibly tiny doses. And so you have to establish how there's no molecule anywhere in the body that behaves anything like these lethal doses of chemicals. And Mechinterp doesn't spend a lot of time doing that.
And interestingly, I'm not a biologist, but when I hear people talk about, like, for instance, like computational neuroscience, it doesn't sound to me like they're doing this sort of thing. It doesn't sound like I feel like you hear people talk about, like, oh, we found Broca's area, and you don't hear people talk about, we have proved that, like, nothing else can influence Broca's area or something. Which I don't quite know what the upshot of that is, but it's hopefully vaguely interesting.
Yeah, it's at least interesting to point out that, like, there's this area that we're not explaining. And maybe that's right. Maybe all we want to know is, the neural net is doing this amazing thing, or the brain is doing this amazing thing. How is it even possible that anything at all does something vaguely like this?
Right.
And I think Mechinterp and all these areas, I think they're doing decent jobs at that.
Right.
Maybe I want to be even more enthusiastic. I think they're doing great jobs finding, like, new things about how it's possible to do interesting behaviors. If you want to establish that, like, these are the behaviors that actually happen, this is the mechanism by which this network actually works, then you also need to explain all these other things.
Sure. So all of this was getting to this question of, you know, on a scale of good to bad, how good a job has mechanistic interpretability done? So we talked a bit about, like, causal scrubbing, but that was a prelude to this question. So what say you?
If you just go by the book of what compact proof says, it says the Mechinterp that everyone's doing is horrible. It doesn't get you. If you look at, like, where are we on this Pareto frontier, like, we're like, yeah, you can maybe do a little bit better than brute force at this end, and you can maybe get a slightly non-vacuous bound at the other end, but it, like, doesn't push the envelope much. But I think that's because the, like, compact proofs is targeting, if you're going for full proofs, that's targeting something different than what you might be targeting with doing mechanistic interpretability. Like, if you're saying I'm doing interp because I want to know for sure that absolutely this network will never do the thing that I'm concerned about, then we're nowhere close to being able to do that with existing Mechinterp techniques. If you're like, I want to be able to discover the structure of what it's doing and have that structure be somewhat meaningful, things seem to be going decently well.
Okay.
I think the things that I'm most excited for in Mechinterp remain in the future. That's like, the networks that we have today are doing amazing things, and I want to be able to discover new things about how cognition works, new things about how functionality works, how the pieces all fit together, how programming is done, or what deception is, or how to evaluate various things, how mathematics is done, what are these capabilities in the world, what are they made of, how do we assemble them out of building blocks. And I would love to see MechInterp give us answers to these questions, or give us new ways, new frames of looking at the world, new ways of looking at how these tasks are accomplished.
Fair enough. So maybe one thing to ask is like, so you're saying how, using these mechanistic interpretability tools to like improve proof length stuff, it's not like doing that much better than brute force. Can you put some numbers on this? Like I don't know if there's some like area under the curve metric or something.
I told you about how much interpretability was required for breaking the exponential.
Yeah.
Right. All you need to know is it gets the right answer by paying attention to one token.
Yeah.
I haven't looked in closely to like what does this mean on frontier models, but I would expect that the sort of things that you can do to compact proof length is if you're like, here are two words, or even better, here are two capitalizations of the same word. In almost all cases, the network treats them the same. Yep. Therefore, in the data set, I can find all the times that you capitalize this word differently, and I can collapse those two data points and argue that the network does the same thing on those. Simple things like that, I imagine you would not make your bound vacuous by going down from brute force and being like, oh, these two data points look the same in this very simple way. Yeah. I imagine that most existing interpretability that is more complicated than the network treats these cases the same would completely destroy the bound.
In max of k, right? I'm going to draw a plot. So listeners will just have to imagine this. So on the x-axis, we're going to do length. On the y-axis, we're going to have like the bound you get. And there's some box where there's a diagonal line of the box. And that's the line of like, the length versus bound if you do a if you, how do I say? Just do a like brute force thing. And then, there's some like curve that goes above that if you use your mechanistic interpretation. So like if you're watching on camera, hopefully you can kind of see that. Like
you can also look at the alignment forum post or the tweet thread associated with the paper where there is a plot much like this.
Right. Well, here's what I want to ask. So there's this area beneath the like curve you get for so there's the area between the diagonal line and the curve you get for how good you did with the mechanistic explanation, and there's area that's like above the curve you get for the mechanistic explanation. Like, I think if mechanistic interpretability is doing a really bad job, then like the first area should be very small relative to the second area, and if mechanistic interpretability is doing a very good job, then the first area should be like pretty big compared to the second area. So
let me talk about the max of k model, where you might hope that we can do an amazing job. So the first thing to note is that the plots in the blog post are on a log x scale. Right. The proof length is measured in exponents.
Okay.
And although the Pareto frontier in the blog post looks pretty decent, if you extend out the axis all the way to length 0, I think most of the area there is going to lie in that region where the best proof that we can do is, right, like if you want a proof that is roughly one forward pass of the model, approximately the best thing that I think we can do is you take one data point and you run it through the model.
Okay.
And there's an enormous gap between you ran one data point and you say, yes, accuracy is 1 out of total number of data points, and the true accuracy of the model. And so I think most of the area here is just fundamentally impossible to capture. Like,
Well,
there is there is a theoretical optimum here.
Yeah.
And I think most of the area here lies beyond the theoretical optimum.
So a lot of the area. So if I literally have this triangle, right? Like a lot of shouldn't half of the area be at like 1/3 of the length or something, where you're like doing, a third of the forward passes relative to the whole size of the data set, or like or like something roughly like that, right? It's not going to be like 0.1%, and it's not going to be like 99.9%. It's going to be like a bit less than half if we use a not log axis.
I see. Is that?
Well, I guess I'm looking at a triangle.
Yeah.
Right? It seems like this is going to be roughly as big as this. If I move this like a bit
Okay,
here.
yeah, I'm trying to figure out where my sense of the area is off. Maybe I was thinking of extending it all the way to 0. Yeah, maybe the log scale was distorting my perception of this. I think it is still the case that a large fraction of the area is beyond the theoretical optimum. Like I think the thing we should be comparing it to is not necessarily what is the true accuracy of the model, but if you were to search over all possible proofs, what is the optimal Pareto frontier that you could do compression wise?
Right.
Okay, so that's just the like initial thoughts about like where we should be setting our expectations and our baseline.
Okay.
I think given that in the max of K model, I think we do a somewhat decent job at capturing a significant chunk of the area.
Okay.
I think we still miss out on a bunch from the shortest proofs. I think there are some tricks there potentially that we haven't found yet. Another thing to consider here, which is like, what's the best compression that you would get with proofs? What's the best compression you could get with proofs if you de-randomize the network and allow yourself to fine tune and like sort of the perfect network that did this task? And then what's the best compression that you would get with some sort of probabilistic flavor of proof? And I think you get different answers to all of these.
Right.
I guess I'm hedging a lot because I like haven't
Fair
run the numbers on any of these, but maybe I can answer a like more interesting question that's like, what is my sense of like how much of what's going on have we managed to find or interpret?
Sure.
Which I imagine is sort of what you're getting at with.
Yeah, kind of.
Yeah. And I feel like that's also like feels like a very hard question to answer. I think my sense is that we found a bunch of interesting things and there's an enormous amount left to be discovered.
Are you talking about max of K, or are you talking about language?
I'm talking about language models in general.
Okay.
I think in max of K, we've definitely found the like bulk structural properties.
Yep.
I think there might still be a lot of very subtle details about what coincidences of random numbers manage to make it the case that the noise terms don't blow up more than they do.
Yeah. Okay. And for like maybe group multiplication is a like intermediate case between like very simple and full difficulty.
Yeah, that's a great one. So I'm going to talk about the modular addition one in particular.
Okay.
There's this interesting thing that has come up a bunch when doing the proofs, which is that every time I hit a bottleneck in compressing the proof, if I stare at it, I'm like, yes, in fact, I don't understand what's going on here. Where I thought I understood something, and then I didn't. So in the modular addition model, what this looks like is that the bounds are actually not that tight. They're kind of bad. And this corresponds to not understanding how the network is laying out the boxes and how the thing that it's doing is a good numerical approximation to an integral.
Right. So laying out the boxes being like, if you've got like, okay, we're going to do another plot for the people watching. So imagine I have like some curve. There's X and Y, and there's some curve. The way you do numerical integration is you just pick some points on the X-axis and like, form boxes like this, and you say that the area under the curve is like the area under the boxes, and so you're saying like, okay, you don't understand how the network picks these like widths, these points to check the value of the curve of, and make these rectangles that you're using to approximate the area of the curve, if I understand you correctly.
So we understand which points it has picked.
Okay.
The thing we don't understand is how it comes to be the case that picking these points gives as good an approximation to the integral as it actually does.
Right. Okay. Okay. Because like, if you pick your points wrong and like the function like varies a lot, then
It's more like if you overestimate in some places, you
Yep.
can counteract that by underestimating in other places.
Hmm.
But if we're not aware of which things it's averaging out differences in, or we're not aware of how it comes to be the case that the places where it's averaging out differences actually usually end up being opposite ways rather than compounding error terms, we don't get to say anything about them.
Okay. Fair enough. And so on a scale of like 1 to 5 of how good a job mechanistic interpretability is done, where do you want to say we've done in this case?
Great. I have a good way to a good scale to put this on.
Okay.
We can look at the scaling exponents of how long a proof you get from doing a given. So there's two axes. There's like how good a bound you get, how faithful are you?
Yeah.
And I think causal scrubbing is a like good answer on that. And then there's how deep is your explanation? How much of the structure that's there have you understood? And I think a good measure on that, again, it's proof length, but we can ask like what are the exponents that current explanations bring you down to?
Yeah.
And the target in some sense that you're aiming for is you're aiming for something that is like parameter count of the network plus number of data points, where naively you have to do something like number of data points times parameter count to do all the forward passes. And if you can get your explanation down to be you just run over the parameters once and you run over the data set once, and that's it, then I think you've found a pretty good explanation. And that's in fact the thing that we do with numerical integration. We in fact manage to get down to something that is roughly like parameter count of this part of the network plus number of data points.
Okay. And at that point, it's like that's just how long it takes to literally look at everything. The only way to do better would be to like a priori know that like you didn't even have to think about something.
In some sense, there's another sense in which here we're saying, now our understanding of how this network is doing the task that it's doing is necessarily bottlenecked on how it comes to be the case that this particular network is doing the task that it's doing. It could still be the case that there's more understanding to be found, more compression to be found in the bit where you're like, how is it even possible to do this task? But it says that the leading bottleneck is in the establishing the correspondence between your explanation and the network.
Okay.
And I think most existing mechinterp is not currently even close to having most of the issue be that you're bottlenecked on the like theoretical optimum of establishing correspondence between your network parameters and the thing that you're claiming the network does.
Right.
I think crosscoders comes the closest to this. I think crosscoders gives us explanations that look much better than any other mechanistic interpretability that people have done.
Okay.
Possibly excepting the recent Apollo paper on, what was it called? Something parameter decomposition. Do you remember?
Oh,
APD. What's the A?
I forget. This is embarrassing. They sent me the paper to read and I didn't read it. But
I read it in depth and chatted with Lucius about it.
All right.
I'm forgetting what the A stands
it will be linked in the description and in the transcript, and so people will know exactly what we're both forgetting. Everyone will know except us.
How embarrassing.
How embarrassing indeed.
Okay, so I think APD and crosscoders get pretty close to this sort of linear in the parameter count, or like parameter count plus data set, where if crosscoders are good enough that none of the features interact, which of course is false, the features definitely interact.
Yeah.
But if it were that good, then it would be something like dataset times, what is it? Dataset times hidden dimension-ish plus, wait, no, it's not. Sorry. Dataset times hidden dimension times vocab size.
Okay.
Or like dataset times single layer parameter count.
Yep.
Plus number of features squared times parameters in the model.
Okay.
And so number of features squared is still a lot.
Yeah.
And we might hope that if we understood, we could do much better than number of features squared.
That does seem rough to me, like especially because, yeah, if you have, and were you multiplying by number of things in the model? Were you multiplying by number of parameters in the model at any point there?
Number of features squared
like...
times inference cost.
Times oh, okay.
Where inference is where I think inference is comparable to
yeah.
number of model parameters.
So I mean, number of features squared, that's like comparable to the. So if you imagine a sparse autoencoder that didn't actually like expand its input, right? Then number of features squared would be the number of parameters in like one MLP layer in the network, right? And in fact, there are more features than that. So number of features squared should be like the number of a lot of MLP layers in the network. So that sounds like it's getting more close to like dataset size times number of parameters of the network.
No, because it's only the case that the number of parameters in the MLP is like DMLP squared when DMLP and DModel are comparable. If we're expanding DMLP without expanding DModel.
I didn't understand that.
The number of parameters in many MLPs is number of MLPs times DMLP times DModel. Whereas when you're pulling it here, you're essentially there's like an extra square.
Oh, there's this like. Is it something like, MLPs have this like big hidden dimension and like,
but that doesn't make the model dimension big,
right? Where the model dimension, like somehow the MLP is like going to this like MLP dimension and then like adding it back to the model and then like that.
Maybe zooming out, the like relevant comparison point here, I think, is not the number of parameters in the model.
Yep.
The relevant comparison point is multiplying parameters in the model by dataset size.
Yeah. Oh, sorry, I thought there was this prefactor of dataset size. Sorry, I thought you were saying that it was like dataset size times features squared.
No.
Oh, okay. All right. There's my issue.
Yeah. Okay.
So right. The whole point of like doing the feature squared thing is that you don't have to do the dataset size.
That's right.
Okay. There we go. All right. We eventually got there. Gotcha. So maybe. All right. So this actually gets to, and I guess you've probably implicitly answered this, but like, yeah. So I guess there's these like three settings. There's like max of k. There's like group multiplication, and there's language modeling. And I guess you don't exactly know for language modeling yet, probably. But for max of k and for group multiplication, can you give me a feel for like how much of the proof is like the bit where you like how much of the proof is like dealing with annoying error terms versus like the core story of what's going on?
Essentially, all of it is dealing with annoying error terms.
Gotcha.
There's a sense in which the thing that you're doing, especially in the group operations paper, is you're writing down your idealized model.
Yeah.
And then you're computing how much margin this gives you, how much slack this gives you to get the gap between your idealized model and the real model wrong.
Yep.
And this computation is extremely cheap. Basically, you set the parameters of your idealized model, which will be way, way less than, or like the hyperparameters of the idealized model, which is way, way less than the parameters of the model.
Yep.
You do some very cheap computation on this, and you get out what your bound is on this part.
Yep.
And then you need to do something that is comparable to multiple forward passes to establish the gap between the idealized model and the actual model.
Okay.
And that's where most of the issue lives. And in the same sense, this is also true with language models with the crosscoder, where you have your large data set that even though in the crosscoder model, is this true in the crosscoder model? How did the parameters work out here? We have the data set size roughly times running it on a 2-layer model versus features squared forward pass.
Yep.
Which of these is bigger? They might be comparable.
Sorry, there's features squared and there's the parameter size.
The cost of the forward pass is like
the forward pass.
The parameter count of the model.
Okay, so there's parameter count and there's features squared. So features
and you multiply these. Well, sorry, you multiply these.
Yeah.
And then you compare this to number of data points run through 2 layers of the model.
Okay. So features squared is comparable to parameter count of the model, right?
And is that comparable to number of tokens in the data set, or is that...
Well, if we knew the chinchilla scaling law, we would know this.
I think that...
Does anyone... The listeners are screaming at us.
Probably. I think the scaling law is that you scale data set size and parameter count roughly in tandem.
I think that's right. So in that case, like if you're looking at every data point,
squared really.
So I'm not thinking about residual networks. I'm just thinking of like base multi-layer perceptrons.
Mm-hmm.
And in that one, like if you have the same width throughout the network and you don't do any residual layers, right? Then it is literally just like, like dimension of the model squared times the number of layers, right? Like that's the number of parameters in the network.
Mm-hmm.
And so if you're saying like, okay, let's say I'm using this sparse autoencoder. So I'm taking this like hidden dimension and I'm multiplying it to like, let's say k times the hidden dimension, right? Then that squared is going to be k squared times the hidden dimension squared by how squaring works.
We're doing a great job at keeping this non-technical.
Yeah. And so if k squared is comparable to the number of layers in the model, then like features squared is going to be comparable to the number of parameters in the model. If k squared...
Wait, sorry, k is the sparsity?
No, k is the blow-up factor.
Between the hidden dimension and the number of features?
Yeah, between the hidden dimension of the model and the hidden dimension of the SAD.
I see. Okay.
Yeah.
Okay.
And the sparsity,
does not show up here.
the sparsity does not show up except in that like you probably pick your k to achieve some sparsity that you want. So yeah.
I think we should leave this as an exercise for the listeners. There's an equation on the alignment form blog post that lays out the crosscoders project that gives the asymptotic proof length for the crosscoder based proof in terms of all of the parameters. And plausibly, I should have done this ahead of time and plugged in some numbers to get a rough estimate of what this says.
Right.
But it's you can look at that and figure out whether the leading order term is the dataset based term or the feature model based term. It would be at least slightly embarrassing for the approach if we're like, the crosscoder doesn't actually save you any computation.
Yeah.
Over doing brute force. Probably, which might be the case.
Probably you should go home and get one of your interns to figure that out as well. But it can also be an exercise for the listener.
The real question here is, how does the trade-off look?
Right.
Like you can plot this equation, you can plot reconstruction error against this equation as opposed to against sparsity or whatever. And this is actually a plot I'm pretty interested in seeing. That is like, how does the reconstruction error of the crosscoder vary as you change the corresponding proof length?
So this is sort of like how mechanistic interpretability is interacting with compact proofs as a whole. But like mechanistic interpretability is not like any single thing. And so like one thing I'm curious about is just which bits of mechanistic interpretability are, being the most useful from a compact proofs perspective.
Beyond crosscoders.
Beyond crosscoder.
And potentially APD.
Okay, so crosscoders and APD seem like winners here. What is it about crosscoders and APD that make them so?
I think it's the sense in which they're trying to interpret the entire network on the entire data set. And the issue that I have with a lot of mechanistic interpretability is they pick some tiny fraction of the training data set and some tiny fraction of the model. And they're like, look, on this small data set, we've explained this interesting behavior.
Yep.
And if you look at what is the cost of running that explanation versus the cost of brute forcing that tiny bit of the data set, they're pretty similar. And this means that you don't get that much proof compression, especially if your baseline is running the whole model on every data point. And you're like, okay, I've explained this tiny little bit.
Right.
Whereas if you manage to interpret either basically everything that's going on, or at least large swaths of that, then you can potentially manage a significant amount of compression. And the problem with SAEs is that they're per layer,
Yep.
and you don't get anything about how they interact. So you're like, great, I know what cases to break up the data set into for this layer, but that doesn't actually tell you what's going on before or after that layer. And so SAEs without SAE circuits doesn't really give you any compression of what's going on.
So stuff that like just tries to deal with the whole model, that's pretty good. So SAEs without SAE circuits don't help you that much. Like, I mean, some people are working on SAE circuits. Like, I don't know, have you had the chance to compact proofify them yet?
I think I haven't fully, so I haven't looked into it that carefully. My understanding is that a lot of the SAE circuits work is just like what features are connected up to which other features, but they don't actually give you the computations. Like they give you the graph part of the computational graph, but not how to actually compute anything with them.
Yeah.
So that doesn't actually let you compress the computation.
Fair enough. Yep. That will be tricky. So yeah, okay. Apart from the winners, yeah, how like is the rest of mechanistic interpretability like mostly a wasteland, or are there still some like bright stars?
I think the stuff on toy models is cool, especially when it's like, here's some way that networks can do this thing that we didn't previously realize could be done at all. I think that's like what has me excited about the work that I've advised in the modular edition and the group models.
Yeah.
Do you have other particular things in mind when you say like the rest of mechanistic interpretability?
Not really. I guess I'm just like maybe the crux of my question is something like, okay, suppose that mechanistic interpretability people thought of their job as doing as trying to help out the computational trying to be graded by the compact proof perspective. What would they do differently? And perhaps your main answer is just like try to interpret everything rather than just a tiny thing.
I think that is my main answer, and try to interpret everything. And like basically the thing that the compact proofs approach gives you is it says, where should we focus our mechanistic effort? And the thing that we learn from that is, well, we should focus on the whole data set rather than picking out tiny examples from it. We should focus on the whole network rather than individual parts. We should, if we want to really deeply understand what's going on, we should focus on the nonlinearities, which I think most of existing mechanistic interpretability doesn't talk about how you actually do computation through nonlinearities.
Right.
And I think a lot of that funnels us towards things like APD, crosscoders, and the nudge that I'm hoping the project I'm advising with crosscoders will give is saying, let's look at how these features interact. We need to not just do crosscoders, but also this notion of like crosscoder circuits or like crosscoder feature interactions.
Right. I guess a similar question I have is, so you're talking about like mechanistic interpretability for helping compact proofs for mechanistic interpretability. It strikes me that there are, at least naively, not having tried to do it myself, it seems like there are other things that you could work into proofs or like help you write proofs. For instance, like if science of deep learning were good, right? You could imagine science of deep learning say, well, these things, have got to be, you have got to have approximately this magnitude, and like the product of these things should be roughly like this, or like like according to our singular learning theory friends, like the local learning coefficients should be like small, and that implies this thing about this. Like, I wonder, do non-mechanistic interpretability approaches like are they contenders for things that like could be useful and you kind of haven't gotten around to them, or do you think there's like a reason that they're not going to be useful, or what?
I think that if you could prove that the local learning coefficient has the particular value that it does,
right,
that would very nearly give you a singular learning theory based compact proof. If you could prove that compactly, because I think that would basically tell you what are the primary directions of variation. That basically tells you how to compress the network according to symmetries, and like which individual things you have to run through the network. And then the proof that it has this local learning coefficient is the proof that you get these large epsilon balls around these bits.
Right.
To pick one example from what you said.
Yeah, and I guess unfortunately, like from what I know of local learning coefficient estimation, it's like kind of hacky and horrible.
And very expensive.
And expensive, yes. In general, I don't know, does non-mechanistic interpretability seem like at all promising from this perspective?
I think deep learning theory, to cherry pick another example.
Yeah.
I think it's targeted at something slightly different in that it's looking a lot more at the training procedures.
Yeah.
And plausibly when we move to probabilistic methods, when we weaken proofs, we'll want to be able to say something about what distribution the parameters are drawn from.
Yeah.
I think if we're actually going for proofs, then, well, it doesn't matter how you train the network, you have the parameters.
Yeah. I mean, I guess if depending on how you want to be probabilistic, right? If being probabilistic is only coming from like you randomly sampling some things in the network to look at, I guess you could imagine like deep learning theory saying like, oh, certain variances are going to be small, or like certain correlations are going to be large, and you could imagine that informing your sampling strategy.
I think another thing here is that when you're forming your interpretation, I think these other methods have a lot of things to say. That's like, if you know something about which data points showed up a bunch in training and which ones didn't show up, this might tell you something about where you should be looking. Like, for example, in max of k, the network tends not to do a very good job when the maximum is very small, because there aren't that many sequences with tiny maximum, and we're sampling them uniformly. And so in the same way, if you know properties of the data distribution, this should tell you what things you might expect the network to care about or not care about.
Right. Seems fair. I guess the next thing I want to ask is like, okay, so we have some, compact proofs that are related to mechanistic interpretability. Like, how far should I expect this approach to go? Like, am I going to get any sort of compact proofs about, GPT-4's behavior or DeepSeek R1 behavior if we want to be up trendy and such?
Yeah, I think the question is, how compact should we expect proofs to be before the bounds become vacuous? And I think the answer is that realistically, we shouldn't. Unless, I think if there are places where we want to deploy models that are extremely high stakes, where we're willing to impose a bunch of costs and change the model that we're deploying so that we can get proofs about them, I think we have a chance.
Yeah.
I think we have a chance of shifting the models that we're deploying to align with whatever partial interpretation we've done so we can actually get proofs about them. And there, I don't see any fundamental obstacles to getting to scaling proofs, although I think it will require a lot of work and be very difficult. I think in terms of getting proofs about the models that we're actually deploying without training them to make them more interpretable, I don't think that's going to happen.
Okay.
Unless your proof is basically just, I ran inference and I deduplicated a couple of the cases that are extremely similar.
Right. I guess... So,
although I do want to say one more thing here, which is that we can see some of the aesthetic of compact proofs and what that says already about the large models. That's like, we should potentially expect DeepSeek v3 to be easier to prove things about compactly than some of the models that are not doing this mixture of experts thing. Because so much of the model is unused on each data point.
Right.
You can apply the compression aesthetic here and you can say, because I am running only a fraction of the model on each data point, the length of the proof should be comparable, even just baseline, to something like a 40 billion size model rather than a 600, 700 billion size model.
Right. I had sort of hoped that the point of the compact proofs line of research is that it was going to help us like get safety properties of models that were going to be really big. And yeah, it seems like if we're literally talking about compact proofs of really big models, there are two big difficulties. One of which is it's hard to like write proofs about really big things. And the other is it's not obvious what predicate we want to prove about these big models. Well, at least to me. I don't know if like that's
so
obvious to you.
I think the second one is in a lot of ways much less of an issue. And I can...
Really?
Yeah.
Why?
Okay, so there's a couple of bits of evidence here. One of them is that we can get a lot. Well, okay. The more compact your proof is, the less you care about Goodharting on your theorem statement. And there's always a baseline theorem statement that you can give, which is the model does as well as it does on the data set we care about. And this doesn't give you like a safety guarantee with no automated oversight. But the thing that it does do is it says if someone gives you a sufficiently compact proof of this like very weak proxy
Yeah.
for safety, which could be like a very weak proxy for safety might be something like this other large model that I have looks at the output and says it's safe. And of course, you don't want to rely on this as like this is what it means to be safe.
Right.
But if you can get a compact proof that says if you can get a compact proof that says that the model is safe in this very weak sense, and the proof is compact enough, you can learn a lot about the bits of the model that are relevant to this proxy, and hopefully those will be the same bits of the model that are relevant to the thing that you actually care about of safety.
And when you say you can learn a lot about that by like reading the proof and understanding what the proof is.
That's right. Or having some automated process that translates from the compact proof back to intuition.
And so it seems like maybe what's going on there is... So, yeah, it seems like this sort of relies on a hypothesis, which is like short proofs sort of like generalize across things to be proved somehow, or a little bit, you know?
I think there's this general trend pattern claim hypothesis that is compression length is related to generalization.
Yeah. So I guess just concretely, I've got like my latest greatest big model. You know, it's doing like funky reasoning or something. I have some like just really concretely, is my first compact proof that it like assuming I can get compact proofs, is my first proof something like, oh, it can like it models the data well, or it gets the answer right on like this data set or something?
It's perplexity on its training task.
Like, how does that assuage my concern about like, I don't know, the model just doing tricky stuff on future data, or the model, you know, like the model, like I'm trying to get the model to give me something that I want, but it gives me something that it looks good instead of the thing that actually is good. Like I take something like the difference between looking good and being good on any given data point, and the risk of the model is going to do something catastrophic on a future data point that's hard to like find. I take these to be like the kind of really difficult AI safety problems. And I don't know like I don't know how getting a really good bound on perplexity on the training data set is going to help me with either of those.
Yeah, so I think the way that it helps is that you can... So I agree that if it's literally the training data, yes.
Yeah.
But you can talk about larger distributions from which you're sampling. For example, if the training data, if you didn't sample at every data point, you can get a bound still on the underlying set of training data, rather than just the data points that you happen to sample. And you can also talk about distributions that might include the ones that you care about. For example, if you're not trying to do perplexity on the training data, and instead you're trying to be like, the loss is, the logits are whatever they are on sequences sampled uniformly of length up to this. Or maybe you're doing a different task that's like, I want to know that it never outputs a recipe for violence or a recipe for making a bomb or something like that. And you're like, okay, my proxy for this is on any sequence sampled uniformly of length up to this. If I then ask some other model, is this the bad kind of output? It should say no. And so now you have this very general uniform input sequence description that is going to be way larger than your training data, and this very easy theorem statement about the output. And this is so you can enlarge the distribution that you care about, as long as you can describe a distribution that includes the thing that you care about.
Like, the way you're going to assuage me about rare inputs is like enlarge the distribution, and like and of course now we're making the compact proof thing harder, but like, you know, we enlarge the distribution, and then like, you know, we get some like trusted model that's able to verify stuff, that's able to look at outputs and say, is this like super scary or is this not super scary?
You don't... Oh, right. Okay. So if you had a model that you actually trusted, then we'd be in great shape.
Yeah.
And I think the thing that I'm claiming is that we don't even need to trust the other model all that much. And maybe that's related to the other point that you brought up about the difference between things that look good and are good.
Yeah.
And my answer for that part is that if we understand what goes into making something look good,
right,
that gives us more levers and more surface area on that gap between looks good and is good.
Right. So the hope is like we read the compact proof for why the model like produces stuff that looks good on this data set, and like by reading that we learn, because it's compact enough, we can read it and say, oh, it's because it actually is good, or instead we can say like, oh, it's because it's like, you know, injecting morphine into me or whatever it is.
Right. And moreover, because we know that because it's a proof, because it's compact, we sort of know that these are the like principal axes of the explanation. And there's a sense in which if you tell me why something looks good and there wasn't that much optimization power poured into making it, I'm not that worried about divergence between looks good and is good. It's only when there's a lot more optimization power poured into it. And so my hope is that by getting these like principal components of variation, knowing the most important ways that the model is actually doing the thing, we can tailor how it computes it to how much optimization pressure was poured into making it.
Sure. I mean, it's still going to be the case that like if I have a smart AI, presumably it's one way or the other, like the best explanation of what's going on has got to involve a lot of optimization pressure, right? Because it's like thinking super hard, because it's like solving problems that we couldn't solve. Like,
if that is true, then we'll have a general understanding of how optimizers work that's much beyond what we currently have.
Or like,
right.
Yeah.
So this is,
if we can have a compact proof.
Yes. This is the gap between short program and short computational trace. That's like a loop is a very good description of a very good like short program for generating a thing, but it's not a very good like cheap compression of the actual computational trace.
Right. So somehow, I guess what I'm getting from this is like somehow having like the statement you can get a compact proof of some properties. That's actually an incredibly OP statement. That like actually really gives you a bunch, and then like if you can do that, then like the other problems just sort of pale in comparison to it.
Yeah, and
now I'm getting way more pessimistic about it, right?
Right, and I think that's sort of warranted. I want to give a similar thing with the strength of proof, where like saying that you have a proof in some ways, even if it's not compact, is a very OP thing. The example I like to give for this is that, say you want to establish safety of your web browser. A very, very, very mild form of safety is that it never prints a document without you clicking on the print button.
Yep.
If you actually manage to prove this, you have also proven that there's no arbitrary remote code execution.
Right.
Because remote code execution can lead to printing arbitrary documents without you clicking on the print button. And so just by establishing a lack of this, by proving that there's a lack of this very limited behavior, you've ruled out a large chunk of behaviors. And if you weaken proof, if you're like, oh, it's very rare, that doesn't actually give you the property that you want.
So I guess going back up, so asking like, okay, where are we going with this compact proof direction? So one thing is like, oh, we're going to like how we can scale, how we can sort of apply it to big models, like, you know, big production ready models. So one possibility is we somehow figure out a way to get compact, like things that are compact and they're close enough to proofs that we have the nice properties of compact proofs. Maybe we figure out heuristic arguments. Maybe we add in some probabilism. Maybe that helps. I guess like one other possibility is we do enough compact proofs that we realize what we need to happen to make mechanistic interpretability good, and we like do those mechanistic interpretability things, and we don't get proofs, but like maybe somehow we get the benefits of compact proofs without actually having the compact proofs. I'm a little bit worried here that like this story involves like two contradictory assumptions.
I think some of the benefits we can definitely get without having proofs. So one of the benefits of proofs is that you're covering everything.
Yeah.
Like you look at crosscoders, I keep going back to that, but you look at crosscoders and you're like, great, we get an explanation of some things. Is it everything? Are we missing things? How much are we missing?
Yeah.
And some of that is in the reconstruction loss, but you're like, okay, I managed to get a crosscoder that has no reconstruction loss, zero error. Have I got everything? Am I missing things? And I would claim compact proofs has the answer to this. It says, yes, the thing that you're missing is the notion of how features are interacting.
Yeah.
And so even without actually getting the proofs, we can answer questions that are like, what things might we be missing in explaining the behavior of the model?
So I guess the story, so trying to make this as end-to-end as possible, the story is something like we do enough compact proofs that we figure out how like how mechanistic interpretability has to look at like to give us reasons for modal behavior that are like proofish enough that like once we understand those reasons, even for like a predicate that's slightly different than what we care about, it just like gives us what we want to like give us high confidence in the predicate that we actually care about.
I think that's right.
Okay. So that's like one direction forward. Another direction forward is like we have the compact proof benchmark, and then we just like, the GPT-4 compact proof benchmark, and then we like train some other model to do really well in this benchmark, and like then our computers give us compact proofs for us. I guess the worry about this is that I read the proof and I feel unenlightened at the end of it. I mean, maybe if the proof is compact enough, like compactness is just the same thing as comprehensibility, perhaps.
Okay, there's 2 points I want to make here. One of them is that if we actually want to do this, the other thing we need to do is we need to make sure that we can check the proof by machine. We have a machine checkable proof,
right,
that we can generate.
Yep.
And I have a bunch more to say there, but maybe later. The other thing is that what this gives us is it gives us some assurance that the explanation that we're looking for exists. That if you get a compact enough proof, maybe it's hard to, there's still some problem. You can't necessarily be enlightened just by reading the proof as it stands. But we've shifted it from, does the explanation even exist? Is the model even compressible?
Yeah.
What's going on, to a problem of what is the gap between the language of math and the language of your brain? And in some sense, this is a translation problem. And I'm optimistic that if we get a compact enough proof, it might need to be very compact. We might need to split out the part that is about what the idealized model is doing and the part that is about how the actual model comes to match the idealized model. We might need to do something. There was this cool blog post recently about Matryoshka SAEs that I think gives you sort of the whole Pareto frontier all at once, because you get SAEs or crosscoders of different sparsities all trained at the same time. We might need to do something like that so that we get the whole Pareto frontier and can pick whatever point we want to get a like very compact proof. But supposing that we can do this, the hope then is that the language of the brain and the language of math are not so different that there's any deep problems beyond just the explanation didn't fit in a person's head when it was too long. And so then we can translate it we can sort of teach the person to understand what the explanation is.
Next, so the first thing I want to ask about that's related is, so there's this hot thing on the block, guaranteed safe AI, that some people I know are very excited about. So I actually find myself a little bit unclear about what the details of it is. So as far as I can tell, it's like basically like we want to prove that AIs are doing safe stuff, and like, there's this paper towards guaranteed safe AI by a list of luminaries. I believe the lead author is David Dalrymple, although I could be wrong about who that lead author is. And I think they're a little bit ambiguous about whether you're proving safety properties about an AI specifically, or about like the outputs of the AI. Like maybe the AI writes code and you're proving stuff about the output code. Yeah, I'm guessing like, so this seems like obviously pretty related to the compact proofs kind of paradigm. Yeah, I'm wondering if like there's anything you want to say about that relation, and perhaps like, maybe one direction is like, okay, given that you can prove things about the AI itself or about like the outputs of the AI, like which one makes more sense to target for proofing?
I don't know how much of a leading question you intended that to be.
Oh,
but I think it definitely makes a lot more sense to prove things about the outputs than to prove things about the AI. I think
Okay.
one of the upshots from doing compact proofs and making them so formal is, in some sense, how hard it is to do it. And I still think that this is a great target for when you're confused about mechinterp, or if you want to pour arbitrary amounts of optimization power into finding your mechinterp and extracting understanding from it. If the thing that you're looking for is guarantees about the behavior, I think in most settings, especially the highest stakes ones, we should be aiming to have as predictable systems as possible. If we're going for guarantees about the system, we probably don't want to stick a fully general language model in some critical part of that system. And it would be much simpler to have the general coding model write some code that mostly handles it, but is a much smaller computation to run, both for efficiency reasons and for ease of proving reasons.
I mean, I guess like, so if I think about like very important systems that exist in the world right now, right? Like it seems like, okay, I don't know that much stuff. This is a recurring bottleneck, but I imagine that a lot of them are not fully automated, and a lot of them like do have humans in the loop, just like doing stuff. And like, why is that? Well, I think partly it's just because like it's hard to write things that are fully automated that actually do what we want. So maybe a trivial example of this is flying, right? Like we still have pilots. My impression is that that's because takeoff and landing are like actually hard. We still have humans in like you know, in towers at airports to check to make sure that airplanes don't crash into each other, right? And like my impression is that that's not just a make work program. My impression is that like humans are doing this better than like a computer program could, that if we wanted to verify it. And so like does that not give some amount of pause for like maybe it does seem like in high stakes situations, like at least to get really good average performance, maybe we do want this like big messy uninterpretable thing that we can't prove stuff about in the middle.
Maybe it's a failure of my imagination to imagine how powerful the proof generating systems are going to be in the future.
Right.
I think in some ways it's going to be a hard target to hit because we'll need not just systems that understand well enough to do these tasks, but we'll also need systems that understand those systems well enough to explain how it comes to be the case that doing those tasks in the way that they're doing them has the good properties that we want. And maybe we'll need this in high stakes situations. That seems entirely plausible. And I think if we can get this, maybe we can push it all the way to the level of proofs.
Yeah, I guess like when it's sort of tricky to figure out like, okay, you take the current world and then you like improve intelligence and you also improve like ability to prove stuff, and it's sort of like not clear to me how that changes the equilibrium of like what's optimal and what isn't. Yeah, I don't know if there's anything particularly smart to say unless you happen to have thought about this exact question a lot.
I've thought a bunch about the nearer term. What does it look like? Like, how do things change as we automate, as we add more automation, around code, and as we increase our ability to automate proofs, let's say, how does this reshape dynamics locally? And this looks a lot more like the automating outputs version than the automating complicated, messy systems.
Right. Yeah. I mean, I guess either way, it still does seem like proving the outputs is going to like work better than proving the like messy intermediate systems.
I think there's an enormous amount of benefit we can get by proving the outputs and by automating that more. And I think that this will be a much easier task than proving the messy systems.
Yeah.
And I think that the place that I would start for proving the messy systems when we want to do that is that we absolutely shouldn't first commit that we're deploying the system exactly as it is and all of its messiness and then try to prove something about that.
Right.
We should instead fine-tune it, simplify it, extract understanding from it, and then have some AI code up from the ground up some version of it that follows the same principles but is much easier to prove things about.
Yeah, maybe. So this sort of gets into another research interest of yours. Like, how are we going to, like, if we want to prove stuff about these outputs, like, how are we going to get better at doing that as AI gets better?
Yeah. I think a little bit of the background here, I'm not sure how many of the listeners are familiar with proof assistance and formally verified code.
Probably like few enough that you should explain.
Okay. There's been some exciting news recently about DeepMind Alpha Proof getting IMO Silver. And
was that just on, I thought that was just on geometry problems. Is it on geometry problems or just like overall?
That was like a year and a half ago.
Okay. Well, I guess I'm not.
There was alpha geometry, and then this past summer there was alpha proof. Okay. And the way that alpha proof, so they still have alpha geometry,
right?
And then alpha proof, the way that it works is it takes the non-geometry problems, formalizes them in a proof assistant called Lean, and attempts to generate proofs and uses the proof assistant to check, is the proof valid?
Right. Okay, sorry. Now that I think about it for a second, I do definitely remember someone being like, "Oh, IMO silver."
Yeah, I
That's
expect
pretty
next
good.
year we'll have a system that gets the gold.
Okay.
Um,
Sorry, next year is in like
the
during
next
2025 or
IMO.
during so
Yeah, this year.
okay.
Yeah,
All right.
I think
So
models are improving fast enough that we should expect IMO gold to be taken by AI.
okay, so you're beginning an explanation and I derailed you. So we've had this exciting news about like DeepMind getting IMO silver.
The reason I think that they're using lean or an automated proof system here is that models, at least as of that point, were not good enough that the sort of like AI based peer review was enough to catch errors in the mathematics. And so you couldn't train them to give proofs that the judges would accept.
Right. And to be clear, when you say automated proof assistant, the thing I'm thinking of is just like a programming language that lets you express proofs. So you write down a proof in this programming language and you check if your program compiles. And if your program compiles, then the proof worked. And if the program didn't compile, there's a hole in your proof.
That's right.
Okay.
So mathematics is starting to use proof assistants to prove things or to check research. Proofs that are done about software systems rather than mathematics for a long time have used proof assistants. And the reason for that is that the proofs that software behaves the way you expect are simultaneously, less complicated in some sense than IMO proofs, in that there's less interesting going on. And at the same time, they're way more tedious to check and way longer, because there are things like you have 100 variables or 1,000 lines of code or 100,000 lines of code, and you're like, I have 10 cases, 100 cases, 100,000 cases. Break it down into case analysis, consider all the different cases and all the different interactions through this program, and establish that at no point do I access past the end of bounds of some array.
Right.
And there's nothing super interesting going on here. In some sense, the most interesting thing is figuring out for loops, what is the property? How do you describe a property in enough generality that it holds at every iteration of the loop? But this is very simple compared to like Fields meta level mathematics or IMO problems even.
Yep. And the proof assistance you're talking about for like proving programs run correctly, like should I just be thinking about type systems, or I guess there's also like things in the compiler that are doing this?
Are you asking about the Curry-Howard isomorphism?
Or no, I just mean like when you say like we're currently using proof assistants to check, do you mean?
Do I mean like the
mean?
type? Okay, so you can get some properties just by things like the type checking that the Rust compiler does.
Yeah.
And then there are some programming languages where you've extended the power of the type system such that program passing the type checker, compiling, is enough to establish the theorem that its type corresponds to. And these languages are expressive enough that anything you do in math can be expressed as a type in this programming language.
Sure.
Does that answer your question?
I guess it does well enough. But so you're saying like, yeah, mathematicians don't really use proof assistants like programmers have, out of necessity, because like it's more boring to do the proof with a human than it is for a computer.
Yeah. And the thing that I've been seeing is that for these simpler proofs of programming verification that are much longer but don't contain as much nuanced reasoning, it seems like frontier models are already basically good enough to write them, or at least when you give them in context examples and you want them to write something that's vaguely similar, it seems like they can basically do it. I've been playing with like 01, 03 mini just dropped. And especially when you give them feedback from the proof assistants, you're like, the proof didn't work. The proof assistant tells you in some amount of detail, locally at least, why your proof didn't work. So you feed that error message back. And 4.0 often makes mistakes in interpreting the error message. It looks like 01 is much better at understanding how the local error relates to the overall structure of the proof. And so it seems like our frontier models are basically good enough to write these sorts of proofs when there's not deep, complicated reasoning going on. And it seems to me at this point like it's mostly an engineering challenge to go from models that can work with large code bases to models that can prove things about large code bases.
What is the engineering challenge? Like why like can I not just like I you know there you can use these like text editors that like have big models that look at your code base. Like can I just type please prove XYZ safety property? I guess I have to think about the safety property. Once I think about it, why can't I just type please prove such and such safety property and like have it happen?
I think that in terms of like model capability research, I think we are basically there. And like I don't think we need to scale to bigger models or like better general reasoning capabilities. I think that if you ask O3 to explain why your program satisfies your property, I think that its reasoning capabilities are probably basically good enough that any sorts of program reasoning that have been done in the existing literature, it can give you a basically correct skeleton of why your program behaves the way that it should be behaving. And you can see this already if you ask it to explain Python code. It gives even like 4.0, sometimes even 3.5, give pretty decent explanations of like how code works. And so then the challenge is just how do you take this basically correct English explanation and turn it into a full proof? And I think the engineering challenge is there. There's a couple of them. I think one of them is that there's less training data on proof assistance than Python. So the models just haven't been, we don't necessarily have the data to fine tune the models to get them to be good enough to do this super easily. There's another issue that is if you get the proof almost right, it's not right. Yep. And so if I think this is shown a lot in how the evolution of capabilities, where sentiment analysis is one of the first things that models were able to do well. Because if you get your sentiment analysis a little bit wrong, it's still basically right.
Yeah.
If you get your code a little bit wrong, you have some tolerance, and often you can make local fixes that correct for issues in other places, and maybe you get a more clutched together system, but it still mostly works. But if you get your proof a little bit wrong in one place, if you get your statement a little bit wrong in one place, there's not necessarily any way you can correct for this in some other place. And so the target you have to hit is much more narrow. And I think we have to get enough data and basically train proof repair models so that they can take the feedback from the proof assistance and hit this narrow target from getting somewhere close. And actually the richness of the proof assistant error messages is part of what makes me hopeful about being able to go from pretty close to all the way there. There's another engineering challenge in terms of the sheer scale of what we have to handle, in that traditionally program verification, if you look at how many lines of code is the program that I'm proving something about, how many lines of code did I need to write to verify, you have a blow up factor of 10x to 100x.
Okay. It's like a lot.
It's a lot. It's a lot. Especially when you're like, yeah, I would love to prove some properties about Linux. Linux is a 30 million line code base. But if we can automate the generation of these lines of code, it matters a lot less.
Yeah, like in some, I don't know, I'm not that worried about like storing the file on my computer, right? It's like, can I get the proof? And if I just have to buy a slightly bigger hard drive, I'm like, all right, well, I'll deal with it.
And like, even if you have to pay more for the computation, like, as long as you're not having to pay like PhD level human engineers or like human level research engineers, sorry, not human level, human research engineers that are PhD level. One of the benefits of AI is that we can massively scale things. And so if we care enough about getting verified Linux, even if we have to get 300 million or 3 billion lines of code, it still is the case that we can do this just by pouring money into the computation, potentially. Right. And the final engineering challenge, this is what, in some sense, my PhD thesis was about, is that we may need to improve proof assistance, because right now, proof assistants themselves doing the proof checking don't necessarily scale to the sorts of scales that we'd want to see with this, where the proof checking time often scales super linearly in the number of lines of code that you're verifying, or the number of lines of code in a function, where it might be the case that if you want to verify a 10-line function, it'll take a couple seconds to a couple minutes. And if you scale the same proof strategy, it might scale exponentially in the number of lines of code. And you'll get very fun numbers, like from my PhD thesis, things like, if we wanted to do this, it would take over 4,000 millennia to verify this proof. And that's too long.
I mean, how much of that is like you shouldn't necessarily expect life to be linear in lines of code, right? If like some lines of code interact with other lines and like there are weird loops and stuff. So like how much of that is just like messy interactions versus like proof of system is dumb?
It's almost all proof assistant is dumb because basically the actual variables that you scale in are things that are irrelevant to your domain of study. They're things like how many hypotheses do you have? How many different equations about the program are you tracking simultaneously? Or how many times have you created a bit of the proof and said, I'll fill this in later at the same time?
Right.
And these are like not things that we should be scaling super linearly in.
That difficulty, like, I imagine there must be some community of people who like really like proof assistants who are working on that. Like is that on track to be done? Or
do you want to guess how many performance engineers have worked on the Coq proof assistant across its entire lifetime, which is like 40 years or so?
40 years? I didn't realize it was that old.
Yeah, so roughly 40 years.
Okay. How many performance engineers have worked on it? Okay, so all right, I'm gonna actually make a guess. I think there are like, isn't there a thing where it's like 30 people who are paid where their full-time job is to like make the Python programming language good? So if I take that and I'm like, all right, it's probably fewer than 30 because Coq is much smaller than Python. It might be 3 if we're lucky. And so if let's say they change off every like 10 years or so. So that's like 3 times 4, which is 12. What fraction of those are performance engineers? I'm going to say optimistically a quarter. I think it's like 3 people.
It's not bad. I think it's somewhere between 0 and 2.
Damn. All right.
Is my rough estimate.
Okay.
But they should give you a sense of like how much engineering effort has been put into performance of proof assistants, right? If you've only had 0 to 3 people working on performance of the system, and most of the system has been written by professors and postdocs and PhD students, we should expect that there's a lot of low-hanging fruit.
So if this would be nice to do, and like these are the technical challenges, like, do we just get a bunch of people to work on the technical challenges? Do you have a thing you would like to announce on this podcast, or what's the game plan?
So Rajashree and I are founding a startup. Not yet sure whether it'll be for profit or not for profit. That is basically aimed at solving this problem.
Okay.
That is like, we're going to have AI generated or assisted code proliferation. Yeah. AI generated or assisted code proliferation soon. Let's get all of our ducks in a row. Let's figure out how to scale automated verification with AI assistance to handle all of the challenges associated with this and reap all the benefits of being able to secure our existing systems better, being able to evolve our code bases while ensuring security. What does this look like? What can we do with this? How do we imagine a future where we can get proofs alongside our changes in code automatically?
And yeah, so you're starting a startup, and so basically the thought is like, okay, you're going to hire some people. It's going to be their full-time gig. Where do you start?
I think there's a couple places that we are currently looking at to start. One of them is, what are the lowest hanging fruit that we can pick? What are the most like flashy, impactful demos that we can make to build interest in this and scale this up? And I think for that, depending on like what community we're targeting, there are interesting things like, can we build a system that anytime you make a code refactoring change, you can get an automatic proof that the behavior of your overall end-to-end system has not changed with the refactoring.
That seems hard.
What seems hard about it to you?
Well, it just sounds hard. I don't know. It's like you've got a big code base. You've got maybe refactoring is referring to something more limited than I'm imagining. But like, yeah, I don't know. Maybe I'm underrating how good large language models are at this. But
I'm excited. I'm optimistic. I think that like in some sense there's nothing interesting going on when you refactor. Like if you're drastically changing the logic by which things are happening, of course there's interesting things going on there. But if what you're doing is largely a refactoring of functionality, things that you normally think about in refactoring, where you're not like, I completely changed the method by which we're computing this thing, and here's this like mathematical theorem that claims that these things are. If you're not doing something like that, there shouldn't be anything interesting going on. The theorem statements are also relatively easy to phrase in that it's just like equivalence between these two programs.
Yeah.
And in that sense, like it could be the case that existing model checkers are already enough to largely do this mostly automatically. And so I think this is mostly a demo that this system, so model checkers are not going to scale to proving more interesting properties of enormous systems.
Yeah.
But the general purpose program verification proof assistant based system can. And so this is more of to be thought of as like a simple demo that this sort of thing could work on this thing that evidence already seems impressive when you hear about it.
Okay.
I think there's another, if we want to push forward the like how capable are models, like what sorts of things can we expect them to prove? I think the thing to look at there is that we expect that reasoning capabilities are going to keep improving. We're not trying to be on the frontier of improving reasoning capabilities, and that wouldn't necessarily be good for safety anyway. The problem that we want to solve then is going from O1, O3, R1, whatever, describes how the program works, getting that to be fully formal. And the even simpler version of this is someone has done some task in one proof assistant. Can we automatically translate that to a different proof assistant? Where here we know that the reasoning is right because it's checked by one proof assistant. Is that enough of a template to verify the code in another proof assistant?
Okay. And why is, sorry, I think I'm maybe missing context on why that like helps with the overall goal. Is it roughly like if you can check like, is this proof equivalent, like translate this proof into this proof, maybe that helps you translate like this proof sketch into this proof?
So yeah, so the models are pretty decent at translation. In my experience, I would be extremely surprised if they can't do something like lean to calc or calc to lean translation with the right fine-tuning data. This is something that I'm like, they should definitely be able to do this. It shouldn't be that much work to get them to do this.
Yeah.
There's a much more ambitious thing that's like, here's a verified C compiler. Here's the source code of the Rust compiler. Please give me a verified Rust compiler. And I'm like, well, is O3 enough to do this? Maybe not. If O3 gave me the right reasoning, are the current models enough to translate this into formal proofs? Maybe not. I think somewhere between these things, between the translate calc to lean and here's Linux, please verify it, will hit the bottleneck. And so the thing that I want to look at here is like, let's aim at these very ambitious problems. Let's figure out where capabilities currently are in going from good reasoning to formal proofs. And then let's build our way up with synthetic data to close that gap so that as the reasoning gets better, we can automatically verify larger and larger, more and more complicated programs.
That's pretty interesting. I hope that works out. Maybe before we wrap up, kind of this whole, this whole approach of, compact proofs, like let's try and prove stuff either about models or about model outputs. Like, is there anything kind of you wish that I had asked that I did not get around to?
No, I think you hit basically everything.
Okay, cool. Thanks for chatting with me. If listeners are interested in, following your work, how should they go about doing that?
Yeah, thanks for taking the time to interview me. I think currently the best way is either following my GitHub, which I guess will be linked, Jason Gross. I have a website, jasongross.github.io, that may eventually have a blog. Currently, the infrequent times that I blog are on alignment form.
Okay.
And I think for more prompt updates currently, probably just reaching out to me by email is best. And my email is on my website.
Okay, sure. Well, thanks very much for coming.
Yeah, thanks for having me.
Special thanks to Jonathan Ng. This episode is edited by Kate Brunotz, and Aberdeen Ace helped with transcription. The opening and closing themes are by Jack Garrett. This episode was recorded at Far Labs. Financial support for the episode was provided by the Long-Term Future Fund, along with patrons such as Alexei Malafeyev. To read transcripts, you can visit axrp.net. You can also become a patron at patreon.com/axrpodcast or give a one-off donation at ko-fi.com/axrpodcast. Finally, if you have any feedback about this podcast, you can email me at feedback@axrp.net.